So, good morning, dear colleagues. Today we're starting our lectures, and our first lecture will be online from Professor Boris Zhukov about the high temperature separation of radionuclides. So, Professor Zhukov, please, the floor is yours.
Good morning. The subject of the present lecture is high temperature chemical separation of radionuclides. This is comparably new approach in radiochemistry, but it is a very promising approach, and I shall demonstrate how does it work in some important cases. What do I mean about high temperature separation and high temperature approach in radiochemistry? First, it is investigation. What is the goal of this kind of approach? The first is investigation of fundamental problems and chemistry of new elements. This is not really connected strongly with the subject of your school of investigations for radiochemistry, but the fundamental things that we studied in Dubna during many years found its application in many fields of radiochemistry, and in particular in production of medical radionuclides, and also production of medical generators for radionuclides. So I shall speak a lot about this fundamental direction. The second item is recovery of medical radionuclides from irradiated targets, its separation and purification. This is the main application of these methods. There are also some different directions, such as I have already mentioned, development of medical generation and fabrication of radiation sources used also for in medical goals, in particular for calibration of medical equipment. Then analysis of products of nuclear reactions in complicated systems, in particular if you irradiate fissioning targets, or irradiate with high energy protons, or irradiate with heavy ions. It's very often it is not possible to understand the composition of radionuclide mixture if you do not perform some chemical separation. The next item is processing of radiation nuclear fuel. This is just technology approach, and it was developed in particular in Russia, in Dimitrovgrad, for processing of irradiated nuclear fuel. Fluorides were used for this kind of separation, but for some reasons, first of all, because of safety reasons, this direction was not developed well and was not applied for real technology. And the last item is radioanalytical chemistry of natural samples. So you know what is radioanalytical chemistry. This is, for example, you irradiate natural samples, some ores or other natural samples in reactor or and accelerator in order to determine small amounts of stable elements. And so you need also chemical separation to reveal the composition of these samples. So I shall speak about mostly about two first items, because they are regularly used in investigations and technology. And other four samples marked black are not used very often. People use it from time to time in some particular cases, but I wouldn't say that this is a regularly used approach. Okay. The first the first way of high temperature separation is the so-called gas chemical separation, where you distribute some elements between gas and solid or liquid phase. Of course, people use such approach during many years, and in chromatography and distillation. But in this case, I present now is complex separation of many radionuclides in wide range of properties and wide range of chemical state. How to achieve the separation? There are, in general, three ways of varying parameters in order to achieve a good separation of the elements of radionuclides. First is varying the temperature. Usually, we vary the temperature between minus 196 degrees Celsius. This is the temperature of liquid nitrogen. It's available everywhere, therefore, but lower temperatures is technically much more complicated. And maximum temperature usually does not exceed 1400 degrees Celsius, because regular resistance furnaces may be used in such kind of experiments and such kind of technology. We, of course, performed some experiments which much higher temperatures, up to, say, 2000 degrees Celsius, but this is a quite rare thing. So usually we work below 1400 degrees Celsius. Why this temperature varying is so effective? Because you know that the rate of chemical reaction depends on temperature as it's shown, as it is determined by Arrhenius dependence. This this dependence is very sharp, and so the volatility of different elements and compounds may change greatly, and thus you can achieve a very good separation of different elements. The ways of variation. And the first evident thing is fractional sublimation at different temperatures. So first you sublime one element in one compound, then you sublime with higher temperature another element, and then another element, and so on. This is fractional sublimation. The second way of variation is a thermal chromatography at different temperature. So you perform chromatography first in one temperature, then in another temperature, so you can extract different elements in at different temperatures. But the most popular approach is the so-called thermochromatography, and I shall speak about this approach a little bit later in details. This means the deposition of various elements and compounds on temperature gradient, and so this approach is the most informative. You can get information and get separation of many elements just in one experiment. There are also some sophisticated approaches as moving temperature gradient, when you provide better chemical reaction with the surface, but I wouldn't speak about this approach now. The second thing that you can vary to achieve gas chemical separation is composition of gas carrier. Gas carrier determines chemical state of the element in the gas phase. And we use different gas streams in our experiments. First, it is elemental state. To achieve elemental states, you use inert gas or hydrogen or vacuum, but sometimes it is not enough to achieve the elemental state. The second thing is using volatile oxides, low oxides, hydroxides, and in this case, we may use air gas, inert gas with oxygen, and in some cases with mixtures of water and some other mixtures. Then, of course, chlorides, oxychlorides, bromides, and special thing is using fluorides, and technically it is more complicated because, as you know, fluorine is a very aggressive gas, and usually you have to work with nickel equipment, and so it is not very popular because of such technical difficulties. And at last, organic compounds. In particular, the most popular is beta dicatenates and some other compounds. But what I would say that chlorides, fluorides, and organic compounds, as for me, it is not so promising because the difference of volatility in chlorides not as high as the difference of volatility in elements and oxides. And the second thing, that if you use elemental state and oxides, you may change this gas composition to change, to make separation first in elemental state, then in oxides, and then again in elemental state. But if you use chlorides, bromides, fluorides, etc., it's very difficult to achieve in one experimental set provide first oxide, then chlorides, and chlorides, because the transition between chlorides and oxides is more difficult than a transition between elements and oxides. So, to my mind, oxides and elements are the most promising compounds for gas chemical separation. And at last, and the most interesting thing, which you can vary to achieve chemical separation, is composition of solid or liquid phase in the reaction zone. This is real chemistry. This is not just sublimation and not adsorption. And varying the nature of sample or nature of column, you can provide a very efficient separation, because for example, deposition temperature may change up to 1000 degrees Celsius in different columns. The same compounds, the same elements, but the difference in deposition temperature may vary in many hundreds of degrees Celsius. So it is different for different elements. So you can achieve with changing the composition a very good chemical separation. How do you use this approach? This is composition of the starting example, of course, because many radio elements may react with the sample material. Then, in some cases, to achieve good chemical separation, and I shall demonstrate some of these cases, you should add some additions, in order to provide sample destruction or the change of volatility of the element. Then chemical filters at high temperature. I shall show you how does it work, and of course material of chromatographic column. So, for example, look at this table, which is composed basing on our experience. Blue is elements who are usually volatile at temperature about 1100 degrees Celsius in hydrogen on Watts column. Green are those elements who are volatile in some columns, but not on quartz column. Quartz column is the most popular high temperature column, and react and appears absolutely not volatile. Red are elements who are volatile in oxygen or air stream in quartz column, but if you add, for example, calcium oxide, some of these elements become unvolatile. And this rose, this pink color demonstrates those elements, though which are not volatile, not in elemental form, not on oxides, but if you heat them in oxygen at high temperature with just small additions of chloride, from example, or gas, they are also volatile. So this table demonstrates how you can change volatility of element, changing the solid phase. In this particular case, this solid state is quartz or calcium oxide. Well, now let us speak about thermochromatography. As I told before, thermochromatography is the most popular and the most informative approach. This approach in radiochemistry has been developed in the late 50s or really in the early 60s. And there are many scientists from Russia, from France, and especially from Germany, who developed this approach for separation of element separation of radionuclides. And I would say that the most important person developing this approach was Professor Ivo Zvara from Dubna. He was my chief in the past. Unfortunately, he died recently. He came from Czechoslovakia, but studied in Moscow State University, and then worked during all his life in Dubna, in Russia, and he is really the father of thermochromatography. What is thermochromatography? This is, in principle, a very simple approach. If you have, as example, heating at high temperature, and some compounds and elements are sublimed, and then you deposit it at temperature gradient at different at different points. So in this first furnace is just for example heating at high temperature, then the volatile elements are transported at a low temperature. One is deposited at high temperature, then another temperature, and then at low temperature. So you can achieve separation of different elements, and moreover, you can understand and investigate chemical properties of these elements. And this is especially important in new element research, where you do not know what other properties of the new element. There are some theoretical calculations, of course, but very often experiment demonstrates that theoretical calculations are far from assumptions. And how to determine, how to evaluate the deposition temperature. Deposition temperature is determined, first of all, by heat of adsorption and also by enthalpy of adsorption and also by entropy of adsorption, and especially in cases when chemical reaction on the surface take place. And I would say that chemical reaction on the surface are especially important for radiochemistry, because radiochemistry works mostly with carrier-free amounts, or as we say, ultra micro amounts, where atoms of the separated element do not feel each other, but they feel only the molecules of gas carrier, and they feel the molecules of the column material. So in this case, this is the case of radiochemistry, and to understand how you can separate carrier-free materials, this is the main goal of thermochromatography. By the way, this is the book of Iva Zvara, and if somebody would like to understand better thermochromatography or new element research, everybody should read this book. It's written in English only, unfortunately. So now let us speak a little bit about the theory of thermochromatography. In this equation, you can see chemical reaction of desorption. Adsorption, one substance is adsorbed, it reacts, or not necessary, but in general reacts with some compound from gas or from solid state, and then there is a different chemical compound in gas state, and also there is maybe another molecule may be formed. So this equation, chemical equation, may be described by differential equation, amount of adsorbed atoms on the surface. It is here. It is N. Is determined by the rate of adsorption and minus the rate of desorption. The rate of adsorption may be calculated in different ways. In equilibrium, it is not important what kind of the rate of adsorption is used. In this case, it is calculated from molecular kinetic approach, and desorption is determined by Arrhenius equation and greatly depends on the temperature. This also depends on the temperature, and this is the enthalpy of adsorption. So if you suppose an equilibrium, thermodynamic equilibrium in this process, this is just a reasonable approximation. In this case, the rate of adsorption and desorption are equal. So you can get a simple equation, and it may be solved. And you can, using some approximations, you can get this dependence of adsorption temperature and desorption enthalpy, and this is desorption entropy. And these parameters are the parameters of experiments, such as duration, period of separation, gas flow rate, temperature gradient, later the parameters of the column, etc. So for a very, very rough approximation, this equation appears that deposition temperature in Kelvin is proportional to the heat of desorption. Entropy, in this case, and entropy is equal for all the compounds of this kind. This is, of course, not correct, especially in the case of chemical reaction. So, nevertheless, having knowing desorption enthalpy, you can evaluate at least approximately the deposition temperature. The question is, how now to determine adsorption enthalpy? And there is a well-working method, is a correlation between adsorption enthalpy and well-known sublimation enthalpy. There, in this picture, you can see such kind of correlation between heat of sublimation and heat of adsorption on quartz columns of different compounds. And it depends how do you calculate entropy of adsorption. This is was approach of Bernd Eichler and Ivasvara, and it works not as well as approach which I developed calculating the adsorption entropy from thermodynamic data. So knowing from this correlation desorption enthalpy, you can predict the deposition temperature, and vice versa. If you have a deposition temperature, you can evaluate the adsorption entropy and thus evaluate the thermodynamic parameters of some compounds and to understand chemical process. Then, another thing, if you would like to determine not just the maximum of the temperature deposition, but to understand how it is distributed. Because you understand, of course, that the efficiency of the chemical separation depends not only on the deposition temperature, but also on the shape of the peak if one peak goes to another, then you should you will not achieve a good chemical separation. So another approach is another task is calculate the peak shape. It is much more complicated thing. Of course, in this case, you cannot consider that the rate of adsorption and the rate of desorption are equal. So it is more complicated thing. There is a Monte Carlo method modeling proposed by Iva Zvara, and this is my kinetic approach. And both approaches are works in many cases. For example, look at this, how it is, you can see calculated peak shapes at for elements with different enthalpy of adsorption. This is at high temperature and this is at low temperature. And this is comparisons with the experiment. This experiment was performed with volatile bromide of hafnium for modeling of element 104 and Rutherfordium. And you can see that experimental results fit very well both with Monte Carlo approach and kinetic approach. So now we shall speak a little bit how does it work for new element research. The first and very impressive application of high temperature chemistry, chromatography, and also thermochromatography was demonstrated by Iva Zvara and his group in 60s and then in 70s, in early 70s, for investigation of chemical properties of element 104, which was called at that time Kurchatovium, but now it is called by as Rutherfordium. Rutherfordium is American name, and Kurchatovium is a Russian name. Unfortunately, the first just physical experiments with element 104 were performed in Russia, but physical results, unfortunately, were not very accurate. So the main method of identification was half-life period, and there was a big mistake in determination of half-life period. But Iva Zvara performed chemical experiments, and actually chemistry doesn't depend on which isotope, which period of half-life do you use. And so he demonstrated that Rutherfordium, or as it was called Kurchatovium at this time, is much more volatile in chloride form than other heavy known elements at this moment, and known at this moment actinides and chlorides of actinides, trichlorides were much less volatile and were deposited about 400 degrees of Celsius and they found that Rutherfordium detected by spontaneous fission goes to a low temperature. Thus was performed the first chemical identification of the new transient actinide element. But unfortunately, as I told, EUPAC agency which determines the chemical names, they do not believe in chemistry. They believe more in physics. And though these experiments were, though this kind of experiments were performed all earlier than Americans discovered, performed the correct physical experiments. Nevertheless, now it is element 104 is recognized as Rutherfordium. So investigation of this element 104, is very interesting, not only because it is just a new element, but because many fundamental physical and chemical things may be understood well with these results. For example, you know the famous actinide hypothesis of Glenn Seaborg, where actinides are F element as well as lanthanides. Now it is, and we consider, of course, this is an obvious thing, but at that point, at 60s, it was not so obvious. Actinide hypothesis was just like an assumption. And this experiment demonstrated that element 104 is the end of actinides, and really this actinide hypothesis works well. Another fundamental thing, very interesting thing, was based on some quantum chemical calculations demonstrating that because of relativistic stabilization of p electrons, 7p electrons, and the split of low energy p half level, and the assumption made by famous American radiochemist Leo Keller that because of this quantum split, element 104 will have not a regular D2S2 general ground electronic state, but as lead S2 P2. So we performed experiment and demonstrated that element 104, Rutherfordium, is as volatile as hafnium in elemental state, and far is not as volatile as lead. So this assumption was incorrect. And when we performed more accurate chemical quantum chemical calculation, we discovered that it is the ground chemical state of element 104 is not as lead, but also is not as hafnium, but something in the middle. But nevertheless, the DS2P, but nevertheless, this is a typical D element because as the result of this investigation, we understood that the D or P character of the elements is not the ground state, and the combination of many electronic states, and nevertheless Rutherfordium is a typical D element in spite of the ground state is some mixture. So back to this Mendeleev table. Another good and interesting result of gas chemical investigation is search of heavy actinides. In this table, you can see that lanthanides are not volatile in most of them are not volatile, but some of them, such as samarium, europium, thulium, and ytterbium, are very volatile. And why does it happen? There is a theoretic approach developed by Johansson, Nugent, and some other, and Charkin in the Soviet Union, explaining this effect. You see, please, the dependence of heat of evaporation along the Z number of lanthanides. You see change dramatically, though usually the properties of actinides are of lanthanides are very, very even. So, and this theory explains quantitatively this situation by the following way. The sublimation of the element or operation of element may be considered as first transition to the gas phase with the very similar electronic states. The in solid state, the electronic state is DS2, and this transition is very even for many lanthanides. It's taken the same. It's called cohesive energy, and it is almost equal for all kind of lanthanides. But there is an electronic transition between excited state in gas phase DS2 and ground state. And in this difference is called promotional energy. And if an atom is dissolved or sublimed, first it is lose the energy and then gain the energy because of the transition to a low electronic state. And this difference promotion energy can be easily calculated by quantum chemical methods. And if you use this calculation, you can determine and to explain the sublimation heat of lanthanides. So people understood how does it works well for lanthanides, and they calculated the same thing for actinides and found that many actinides should be volatile according to this theory. And we performed gas chemical thermochromatographic investigation on metallic titanium columns and also on molybdenum columns and niobium columns, and demonstrated that heavy elements, californium, einsteinium, fermium, and nobelium, and mendelevium are really very, very volatile, just following this theory. So this is very important things to understand what is volatility and how can it be explained and how can it be calculated. Of course, it may be used in different fields of knowledge. So it was this understanding this approach was used also for some preparation of sync sources and targets, accelerated targets. So it works also for some applications. So another interesting element which we investigated is element 108, which now is called hessium. This element is this element is analog of osmium and ruthenium. So we suppose that it has volatile tetraoxide, and so we performed online experiment radiating californium targets with neon and performing fast gas chemical separation at high temperature with calcium and quartz filter, removing alpha emitters such as polonium and actinides, including volatile actinides, and so depositing osmium and, as it was supposed, also element 108 on the surface of lead, where lead reduce volatile gaseous oxide to non-volatile dioxide. So this experiment was very efficient, and this is the most fast chemistry performed so far. Having high temperature and high gas rate, we performed this very selective chemistry during 50 milliseconds, and this is the best achievement so far. So chemical separation can be done for such short time. But unfortunately, we didn't found element 108 because the radiation was not too long, and the nuclear reaction was not very well. But later, our German colleagues and Swiss colleagues, they repeated this approach with in thermochromatography, and found that really hessium is volatile in tetraoxide form, but it is less volatile than osmium. First, people didn't understand why, but later we calculated that this reaction of reducing volatile oxygen works not only on lead, but works only in comparably in inert surface, and so it found this explanation. So now people work on the much heavier elements, such as flerovium, and analog, very volatile and analog of lead. This is our colleagues in Dubna, and cooperation with Switzerland, and our friends and competitors in Germany. And this investigation of new elements also provides some fundamental understanding of the properties of heavy elements and the role of the so-called relativistic effects in their chemistry. Why are they so volatile, and are they really so volatile as predicted by the theory? And in this gas chemical approach demonstrated that it works very well for understanding the fundamental things. And you can see what elements were investigated, which new elements were investigated with this gas chemical approach, what compounds are used, chlorides, elemental form, bromides, oxides, and hydroxides also. So far, these elements were investigated up to Copernicium and flerovium. Now let us speak at last. We have not so much time, unfortunately. But now let us speak about the application for nuclear medicine, in particular for production of medical radionuclides. So, what is high temperature approach used in nuclear medicine? First of all, it is production or isolation of radionuclides, medical radionuclides from irradiated targets. Widely used is isolation of iodine-123, which is a very popular medical isotope. Then a new, very promising isotope is astatine, which is usually produced from and isolated from business target and irradiated by alpha particles. And it may be produced also by a different way. And at last, the production of strontium 82 from metallic rubidium targets. This is not gas chemistry approach, this absorption from metallic liquid targets on the surface. So these investigations resulted in regular application in technology and regularly obtaining these medical isotopes. There are a number of other investigations, and they were successfully, but they were not used in technology for regular production. Maybe it will be used later. This is obtaining astatine from thorium or uranium targets, selenium 70 production, selenium 72, and radium 223, and germanium 68. Let us get into some details. In this, on the top of this slide, you can see the methods of production of iodine-123. All of them are used gas chemical approach. First is irradiation of enriched xenon, which decays into short-lived cesium, then to xenon, and then to iodine. So irradiated xenon is pumped to some vessel where it decays into iodine, and then enriched xenon is pumped back to the target shell where it is irradiated again. So after this, you wash up iodine and use for medical diagnostics. Another approach, which is used also in many facilities, many institutions, is in irradiation tellurium target with low energy protons for producing iodine 123, and then heating this target at high temperature, 700 or 800 degrees, to evaporate iodine. Then, at last, is a very productive method and also used, but not very widely because not so much accelerators of this type. So in this case, melted sodium iodide target is irradiated, and xenon 123 is isolated from this melted target on line, and then decays into iodine 123. So this approach also works well. Another thing that also was successfully used is production is a very popular medical isotope, germanium 68, used for calibration of PET scanners and for fabrication of gallium 68 generators. So people irradiate metallic gallium target, and then after dissolution, they sublime germanium from gallium in the form of chloride, and then in the form of germane, very volatile but enough stable compound. And this approach can be used also for preparation of calibration medical sources, and also the obtaining of this very popular isotope. And in this slide, you can see how does it work a separation of chemical separation for obtaining astatine. Astatine is a very prospective radionuclide for therapy of many cancer diseases, and usually people irradiate bismuth target and sublime astatine from bismuth targets, but there are some impurities of polonium 210, and this isotope became, of course, very popular after this criminal case in London. So people want to have a very good separation from polonium, and this separation may be achieved on by separation on high temperature process and on calcium oxide column, because polonium is also volatile, but it is completely absorbed by calcium oxide at high temperature. Another method of producing astatine is irradiation of thorium targets and uranium targets. And there are a lot of radionuclide impurities, including volatile impurities. So in order to separate this astatine from these impurities, selenium, bromide, iodine, you can perform thermochromatography, and you see that you can get a very pure astatine even in this awful nuclear reaction where half of periodic table is formed, elements of half of periodic table. So this table reminds you how we some elements volatile in oxygen may be absorbed. This is polonium, also, and tellurium may be absorbed by calcium oxide. Another good example of chemical separation is obtaining radium-223 from thorium irradiated targets. And you see here thermochromatography on metallic titanium column with addition of metallic lanthanol. In this case, metallic state of these elements, rare earth elements, is realized, and so it may be separated from other elements. So we heated the sample or irradiated thorium with lanthanum at high temperature, and then separated on temperature gradient. Most of the elements will stay in the this crucible, and some of them will be sublimed, will be deposited at high temperature, some of them will be deposited at low temperature, and this is a very good approach for chemical separation of radium-223 from this target. Sorry. Sorry. Я сейчас не могу говорить на лекции. Another example, a good, very impressive example is obtaining selenium-72 from irradiated gallium arsenide target. Selenium-72 is a very promising isotope as a generator of arsenic-72. And arsenic-72 is a positron emitter, and it is very difficult to separate and purify selenium from large amount of arsenic. And if you use just sublimation at different temperatures, you can see that arsenic and selenium is sublimed at very similar temperature, as well as zinc impurity. But if you add metallic iron to this composition, then you can find then zinc is sublimed at much lower temperatures. Selenium is sublimed in this temperature range, but arsenic is not sublimed at all because of chemical interaction of with iron. This was a very efficient chemical separation, and also demonstrates that gas chemistry approach is not just sublimation or adsorption. It is really chemical approach. Another example of good application of gas chemistry for medical use is analyzing of products in complicated mixtures. In this case, we investigated the products after irradiation, antimony, targets in order to produce tin 170M, a very promising isotope for both for diagnostics and therapy, for theranostics. So we heated this sample in air or helium stream, and most of volatile elements, including target material, was sublimed, and antimony was unvolatile. Especially it works well with air, and in helium there was some sublimation low oxides. So we, for investigation of cross section, we irradiated in one furnace up to 12 samples, different samples in different tubes, and then measured and analyzed the products with germanium, pure germanium detector. And the most impressive result, of course, it is not gas chemical approach, but high temperature approach, is production of strontium 82 from metallic rubidium targets. First, people started, this was the most efficient target, of course, to irradiate rubidium with protons from 70 MeV up to 100 MeV. And in this nuclear reaction, strontium 82 produced. And strontium 82 is a very promising, is a very good isotope for making rubidium 82 generator for PET diagnostics, cardio diagnostics. So people first used dissolving metallic rubidium in some solutions, in alcohol solutions, and then transferring it to some water solutions. But this procedure was not very effective because of some small explosions, some fires, some losses, etc., etc. But we investigated the sorption of strontium directly from metallic rubidium, and we found that there is a very interesting chemistry. For example, the temperature dependence of in different surfaces is very strange. When you increase the temperature first, adsorption goes down. So of course, as it should be, at higher temperature, desorption is lower and the adsorption rate is lower. But then at higher temperature, it increases very much and achieves 100%. And then we investigated these processes and found that this happens because strontium exists in metallic rubidium in some form of oxides and on colloid particles. And then at higher temperature, this oxide colloids are destroyed and adsorption becomes more effective. So colloids were mostly in the lower part of the target, so adsorption is here. So this interesting results came into regular application in industry. First, it was uh, applied in Russia, in Obninsk, and then it is regularly used in strontium production at Aronnax. And so this comprehensive approach, sophisticated approach, works very well, not just for investigation, but for regular production. And in the future, we are going to install online production where metallic liquid targets will be irradiated in high beam current accelerator, and there will be online extraction by adsorption from liquid rubidium in the hot cell. So you may irradiate and extract strontium at the same time. So there is a project, but if we found some funding for this thing, then we should produce a lot of strontium. So this approach works very well, not only for metallic rubidium. Another example is production of palladium-103 from metallic silver target. And we tried this process also for metallic, for liquid melted metallic silver, and it also works. And you see in this example that these platinum elements, which are very close in chemical properties, nevertheless absorb on tantalum foil in a very different way. Palladium does not absorb and is not absorbed, and rhodium and ruthenium is well absorbed. So you can purify palladium by this method from these impurities. Of course, it is maybe not very well for regular production, but an interesting result. Another interesting result is adsorption of different elements or radionuclides from liquid lead. Liquid lead demonstrated that the chemistry is quite different than in the cases on metallic rubidium and metallic silver. And we found that different elements are very selectively extracted from liquid lead by different surfaces. For example, tantalum selectively extracts iridium, but does not absorb platinum. And platinum is absorbed on aluminum. And molybdenum technetium is absorbed by quartz. So of course, molybdenum is absorbed by metallic molybdenum and hafnium by titanium. But this demonstrates that sometimes it is very interesting chemistry. Why does iridium is absorbed on tantalum, but platinum is not absorbed? So this approach may be used for production of medical isotopes, where liquid lead, or better lead bismuth eutectic is used for cooling of nuclear reactors. So you heard that there is a great international project called ITER. This is thermonuclear fission reactor, and they used this liquid cycling system for cooling of this reactor. So there are a number of different isotopes, medical uses produced as a byproducts, and you may extract these medical isotopes by this way. And at the end of my presentation, I can tell you also some application of high temperature gas chemical approach for medical radionuclide generators. Long ago, people found that molybdenum, that technetium is very well is dissolved from irradiated molybdenum oxide in the form of technetium oxides, and especially in the form of technetium hydroxides. So if you heat irradiated molybdenum at high temperature, it is about 800 temperatures or 1000 temperatures, so you may produce technetium and use it as generator. Another similar thing is tungsten rhenium generator. It also was tested, but both this and this unfortunately was not applied for regular production technetium and rhenium. But this generator, this new kind of generator, which I have already mentioned, is selenium-72 arsenic generator, is a new thing and a very promising thing, because arsenic is a PET radionuclide and very interesting radionuclide. You may label many organic compounds in it, and so different kinds of generators based on gas chemical approach may be used. In Dubno, they used arsenic sublimation from HCl solutions, and we use reverse generator scheme when we removed selenium from the surface of manganese dioxide. We use different dioxide, but of course, different surfaces, but manganese dioxide demonstrated that this is the most efficient for this kind of separation, for this kind of generator. And at last, this is our last development and will be published, I hope, in this year, is actinium bismuth generator. It is based that bismuth is much more volatile than actinium, and heating it in inert gas flow with addition of H2 with hydrogen, you can get a very pure bismuth in one bismuth 213 in one stage. But again, this is just investigation. And also, gas chemical approach may be used for fabrication of germanium 68 sources, as I told. Especially, we used it for production of linear sources when we sublimed it in volatile germanium H24, and then decompose it at high temperature, about 300 degrees, with a very even distribution used for calibration. So, finishing my presentation, we have 5 minutes for questions. let us finish this lecture again with this table demonstrating that almost all elements of periodic system may be separated with gas chemical approach, especially as elements, as oxides and low oxides. And if it may be sublimated, then it means that it can be separated. If even they have absolutely similar heat of evaporation, nevertheless, using solid, chemically active solid state, you can separate very similar elements such as actinides, lanthanides, or as I demonstrated, selenium and arsenic, which have very similar sublimation parameters, but chemistry is different. So it is a very promising approach, especially for people, for students that would like to get something new and not just traditional chemistry such as ion exchange or extraction, etc. This investigation of this kind needs, of course, some more technically sophisticated equipment and better understanding of the process. But you're welcome if you join to our small team, or the team in Germany, the team in Japan, the team in the United States, where these kind of investigations are more and more popular. Thank you very much.
Thank you. Maybe just a short question. From me, what are typical times for the separation with these methods?
If you use it for production of medical radionuclides, it varies from half an hour to 3 hours, something like this. But in some cases, if you need very fast chemical separation, it may be as fast as 50 milliseconds, as I demonstrated. 50 milliseconds. My calculations show that maximum what can we achieve is 5 milliseconds. But 1 millisecond, I do not believe.
Okay, and there is another question. Just thank you for the detailed presentation. So, and yeah, thanks again. We're finishing with your lecture. Thank you.
No questions anymore. Yeah. Thank you.
So, Professor Ojovan.
Yes, good morning, everyone. Let me a little bit manage things here on my screen, and then you will give me the possibility to share my screen. So then we will go to my presentation. So it works. Thank you very much. So perhaps now you see the screen, right?
Yeah, now it's perfect.
Okay, many thanks, Professor Petrov. So dear colleagues, now it's the next lecture. It's because we work, but we produce some waste. And in the case when we work with nuclear energy, or even with some natural materials, then a part of the waste, it is called radioactive waste. So we call it also nuclear waste. But the focus of lecture is on radiopharmaceutical waste, which is radioactive, so it's also radioactive. We have with you for my lecture 75 minutes. And yesterday I agreed with organizer that we will make a short break in the middle somewhere, because otherwise it's too long. And it's difficult, you know, to focus the attention for such long time. So somewhere after maybe some 40 minutes, something like that, we will make a short break. You may think about some questions or anyhow. Yes. So oops, doesn't work. Once again. Oh, now it's okay. Dear participants, here is the content of my talk, of my lecture. So I will go from topic to topic. I put here on the right hand, you see here a cover of a book, and this is actually the third edition of this book. It's not for advertisement, because it can be considered I'm one of authors of this book, but this is actually the main reference for radioactive waste management. And the first edition was published in 2005. It is used in the United Kingdom in universities and not only. And it's focused on radioactive waste management, and it was created on the basis of teaching the module on radioactive waste management in United Kingdom, where there is a nuclear technology. It is this picture in the slide, Nuclear Technology Education Consortium. It is where all kind of modules are taught to students related to the application of nuclear energy. Nuclear reactors, everything, accelerators, all kind of applications of nuclear energy. And the module on radioactive waste management was I was the director of this module, and based on this experience, we published first edition, and nowadays the third edition, this one. Yesterday, I arrived from China, and this book is now under translation to be published by Chinese and in Chinese language for the usefulness of the student in China. So that's why these pictures are here, not just, you know, to do a kind of advertisement. Okay, so we start our lecture introduction with the definition of radioactive waste. You see here, radioactive or nuclear waste, it's a waste. So it's a material that nobody needs. We throw, we produce other kind of the waste and care very, very little about it. So later on, this waste is collected, maybe municipal waste is treated somewhere, maybe not. Anyway, it's a material that nobody needs it, because of that is waste. But when we come to radioactive waste, look to this definition. So, is a waste that contains or is contaminated with radionuclides at concentrations equal to or greater than the clearance levels established by the regulatory authority. And it is taken from the basic safety standard used in nuclear energy everywhere, not just in radioactive waste management, everywhere. Since you are already specialists, reminders, not because you don't know that. In reality, the usual waste, the trash that we throw away and forget about, it also has some radioactivity. Everything around us is a little radioactive. Even our body contains, let's say, carbon-40 that is used for historical living objects dating, after all, because after the organism stops functioning, then the content of carbon-14 decreases to zero finally. Now it's due to the decay. Otherwise, it would be the ratio of carbon-14 to carbon-12 is constant. So when the content of radionuclides is higher, we don't say background. There are some clearance levels established everywhere. The recommendation on these levels is given in this basic safety standard published by IAEA, and only if the content is higher than these levels, only in this case we say this is radioactive waste, this is nuclear waste, and then all kind of regulations are in place and we need to care about. So we move to the language of classification of nuclear or radioactive waste. And this is again, regulations are dominated by the activities held at International Atomic Energy Agency. And the agency published a safety guide on classification of radioactive waste and introduced for the use. It was introduced before the agency, but agency is harmonizing in the world all kind of this terminology, standards, technologies that are proven and approved and then recommended to be used everywhere. So the language of characterizing the radioactive waste. So classification. We start with the exempt waste. This is namely this trash. This is the waste which has nothing to do with regulations by regulatory authorities, because the content of radionuclides there is below these clearance levels. So we understand that there is some radioactivity everywhere. There are some we call it background radiation. Can be just radiation coming from the outer space, but can be the radiation coming from the walls, from other bodies, from our colleagues, from ourselves. And you know, this even banana, it's a lot of potassium 40 there along with the stable potassium. And because of that, we are continuously radiated. But this is exempt waste. The content of radionuclides is below clearance levels. So that's one. Then we have very short-lived waste. This is namely the waste which is in, radiopharmaceutical. Most of the radioactive waste produced by application of nuclear energy in biology, in nuclear medicine, it's very short-lived. So the half-lives are very short, and then we can afford to store this waste, and then naturally it disappears as radioactive waste. Then we go to the very low-level waste, and this is the waste which we have clearance levels. Each radionuclide has its clearance level. Then, if you find the radionuclides above the clearance level, we say this is radioactive waste. But maybe it's not so hazardous as high-level waste. We will come to it. And if you are a little bit above the clearance level, and a little bit above can be 2 times higher, maybe 10 times higher, but still not very, very above the clearance levels. We understand that the hazard of this material is practically negligible. It's not real hazard from there. And in order to not spend our resources, which are not so plenty resources and so on, vitrifying, let's say, very low level waste, the IAEA introduced this very low level waste. It's above the clearance level, but not very much above. So the hazard from this waste is not very high. Then we go to low level waste. And here is the place to tell you what kind of parameters agency is recommending to use everywhere for classification. So this is on this plot. Look here. So this is the activity content that goes vertically, higher and higher. And horizontal is the half-life of decaying radionuclides. And if these parameters are such that the waste can be disposed of near surface, it means that the total time required for the decay to the background levels or to the levels which are below the clearance level, it's few hundred years. We understand, we know from the history, from experts in geology and so on, that during few hundred years, very, very significant things do not happen in near surface layers of the earth, on the surface, and we can have a very high confidence on the behavior of materials during these 100 years. So this is low-level waste. We can dispose this waste in you see here now in this picture, this classification scheme, that this is low-level waste. It is for near surface disposal. We can go deep underground. If such possibility exists, yes, but it's extremely expensive. Most frequently, it's extremely expensive. So it is allowed, and practically everywhere this is near surface disposal. Then we go to intermediate level waste, something which is, let's say, the storage time is thousands of years. Then we understand that it's not reliable to dispose of this waste in near surface repository. We need to go deeper. Maybe not yet to go very deep into the geological formation, which are stable and so on. So not to be very expensive, but it is not allowed to dispose of in near surface repository. So this is intermediate level waste. Finally, we are coming, so we go to this part of the plot. This is high level waste. This is the waste where, due to the either extremely high content of radiation or to the very long lifetimes of radionuclides, so we shift into this direction. See the curve shifting here. We need to go somewhere where we have stable conditions, so stable that they are stable on geological time frames, because only these times will suffice for the full decay of radionuclides. And then you see here some pictures, how they look like. So looks like trash, let's say, from the outside, but due to the radiation here, let's say it's a canister with radioactive waste, and the picture looks nice, but the radiation is so high that the doses are immediately lethal from such kind of the waste. And in addition, this waste also generates heat. So now we move to the chapter 2. This is about nuclear fuel cycle and non-nuclear fuel cycle radioactive waste. So it's a map here of the countries on the globe, and in red color there are countries which operate nuclear power plants. So they produce the energy in a very clean manner. I'm not speaking about the catastrophic accidents that occurred with the nuclear power plants, but confidently speaking, the consequences are of course very considerable, but nevertheless not to stop using nuclear energy, which is the cleanest thing. Compare with all others. Even if you take the uranium generated, it's many hundred times more uranium in the piles of the ash which is burned by the plants that produce energy, burning the coal. It's more uranium there, if you compare it with the uranium in nuclear reactors that operate now in the world. So who is contaminating more the environment? That's by the numbers. It's unfair to say that this is done by the nuclear energy. Of course not. So then we have research reactors. You see by another color, purple a little bit, research reactors, and then we have practically everywhere these used sealed radioactive sources. So these are the materials, the nuclear energy, which also produces waste, and then we need to care about the waste. And there is a nuclear fuel cycle. What is a nuclear fuel cycle? We start with the ore. We extract the uranium from the nature, and then we process this ore, and then we produce fuel. We use this fuel in a reactor. So this is operational phase of nuclear fuel cycle. And then we come to the spent nuclear fuel or used nuclear fuel and some waste, which is produced by the use of nuclear energy in producing energy. And all this chain, it's nuclear fuel cycle, because we can dispose of the nuclear fuel or reprocess it and use again the useful uranium. And then it's indeed something like which is a cycle. And the last part of nuclear fuel cycle is called back end of nuclear fuel cycle. But nuclear energy, it is used not only to produce energy, so to generate electrical power, maybe to use for desalination, for other purposes. We have, you see here, research reactors, right? It's use of nuclear energy. And research reactors are used also to generate, and from this school, you are focused on use of nuclear energy for medical application and so on. Then we have some generation of some waste. And this waste has nothing to do with the nuclear fuel cycle, right? Because of that, there are other terms, institutional waste, something like that, that very often we say non-nuclear fuel cycle waste. So it's the waste which appears not in the nuclear fuel cycle. It appears due to the use of nuclear energy in agriculture, in the industry, in the medicine, in the research, biological research, in geology also. So in other than nuclear fuel cycle. So this is non-nuclear fuel cycle waste. For the nuclear fuel cycle waste, this is actually the picture that again schematically shows. So things start with mining, then we got milling, then conversion, enrichment, we produce the fuel fabrication, we operate the reactors, and the reactor produce spent fuel and some waste. And then we can dispose of this nuclear fuel. It is like United States of America is doing, it is like Finland, it is like Sweden doing, but other countries like United Kingdom, like Russian Federation, they reprocess the fuel to produce new fuel, and then you see it's indeed something like cycle, right? And here in this column, all kind of the waste, and now you see what is high level waste, intermediate waste, low level waste. It's a picture that describes the waste generated in this column by nuclear fuel cycle. What about non-nuclear fuel cycle waste? So this waste is generated in hospitals. Then radionuclides are used for diagnosis, for treatment, and so on. Universities, some research they do that. So we are now in the Moscow State University Radiochemistry department, the main department or division, how they call it. That in Moscow State University, it is giving education and training in the area of use of nuclear energy everywhere, including nuclear fuel cycle, of course. Research laboratories, many more, they can be with the nuclear research reactor without any way. Oil and gas industry widely use nuclear energy to control the quality of the oil and gas produced and so on. Some non-nuclear industries. So this is a schematic of an apparatus that control, let's say, the level in some from chemical industry, let's say, the level of some very hazardous liquids inside of the vessels and so on. This is a picture that shows a gamma knife for a treatment of patients that got cancer in order to save the lives, to extend significantly the life of these patients, and so on. So here, this is a small detector. I forgot already in your room, if you look up. in my house, I don't have this, but very often, even in private houses, we got small detectors that will give alarm that there is smoke, there is fire hazard, maybe CO emission. So this also, it is using radioactivity inside. And here information for United Kingdom, about 5,600 users of civil sites in England and Wales, and 9,000 in Scotland, 150 in Northern Ireland. So they all produce in small amounts, nevertheless radioactive waste. And here in this slide, examples of different kinds of the radioactive waste you see here. And if you speak about by the volume of high-level waste, this is just 1%. For very low-level waste, you may expect that it's very, very large amount. And in reality, it's also very small amount. Most of the waste globally, if you look to the volume, this is low-level waste, 96% on average. And about 2%, this is intermediate level waste. So here's some textual information about the typical sources, typical examples of level waste, intermediate level waste, high level waste. So these are coming from the processing of nuclear fuel. So let's move further and speak about the radiopharmaceutical waste. Because radioactive materials, nuclear energy is used in medicine, and it is used for diagnosis, widely used in large hospitals, for therapy, used also for research. And then we have different kinds of the assays. So radioassay for clinical diagnosis to identify, the organ in the body which needs treatment, which need attention. And then even unsealed radionuclides are used. So the radionuclides that are in solution, maybe solution that means liquid form, maybe gaseous form. So we are investigating the lung of the patients. Clinical diagnosis, therapy, medical research, unsealed radionuclides. For radiotherapy, sealed radioactive sources. So it's a case when the radionuclides are encapsulated hermetically in some capsules, but the radioactivity can be extremely high. And then we have this again, or they can be implanted, or they can just produce a beam of typically gamma rays that then is focused on the tumor, and in such a way the patient is treated by intensive beams. Because of that, this device often it is termed gamma knife. And the radionuclides have the property of deconcentrate. Maybe that this is picture taken from an overview with the reference given here. It is to inform you that what first of all is, I believe you already know that, but this is radiopharmaceutical. What is that? So it's a pharmaceutical product, but it is labeled by a radionuclide in its composition. And because the radionuclides have the property to be concentrated in certain organs of the body, and here this overview paper informs about the preferred organs in a human body where the radionuclides, and in such a way we can use this property of radionuclides and also use in parallel the properties of medicines, of pharmaceuticals to be concentrated in certain organs. In such a way, we can do either diagnosis or treatment, concentrating the nuclear energy in this organ and then identifying that organ is functioning improperly or the tumor is in a certain part and so on and so on. So either for diagnosis or for the therapy. And you see here plenty of radionuclides, often technetium-99 is already noted, which is used for that. Then once we use the radionuclides, then some excretes from the patients, then some materials that are in contact with these radionuclides, they become annealed after the use. Some radiopharmaceuticals that were already used. So we are generating waste, and the waste contains radionuclides. And then we have the risk associated with the presence of radionuclides in these radiopharmaceuticals. So in such a way, we have to deal with radiopharmaceutical waste. And because of that, there are special rules, special instructions, advices, how to proceed when we need to deal with radiopharmaceutical radioactive waste. So we cannot simply throw them and use the same approach as for other waste which is non-radioactive, because the concentration of radionuclides can be quite even high, much above the clearance levels. It depends again. So if you are close, we will have very low level waste, if higher than low level waste, and so on and so on. And again, International Atomic Energy Agency, it is collecting the information, collecting the practices, collecting all kinds of the experience accumulated in the world when we have to deal with these kind of materials, these kinds of radioactive materials. And here is the slide that informs us. There is a kind of human health campus. The link that is provided here in my lecture. Yesterday I submitted to organizers the file with this lecture. Anyway, nowadays it's so easy. If you have a little bit hint about the information, it should be there and there. Through the internet you can find, and the question is just to find a proper site. And IAEA, this is the most reliable place really to find reliable information. No, not speculations, not advertisement, not something which is, a kind of propaganda of things that can kill from everything, but in reality, who knows what is that? So commercial interest, other interests, everything which comes from IAEA, this is reliable. And please, if you need relevant information and if you need reliable information, address IAEA websites. So you see here the radioactive waste management on Human Health Campus. Then you have a kind of chapter, a kind of information about radioactive waste management. What to do, how to proceed. So you see here, all radioactive waste must be carefully sorted into different categories. Each of them have certain processing requirements. So we have in this radiopharmaceutical waste radioactive material that is no longer useful. So because of that is waste, and we need to do something with it. Items that have become contaminated. So some paper, some plastic gloves, some covers, counting tubes, glassware, washing liquids, excreta from patients. Because if they consume the radionuclide, there is another half-life. It is called biological half-life. This is a half-life for radionuclides. How long they are present, dwelling time, and human bodies. This is already known from experience, and based on that, we know how long that, let's say, tritium is evacuated from our body and all other radionuclides. So the excreta from patients to whom radionuclides can be administered then also should be collected, and this is a kind of radioactive waste. Now, the radioactive materials in medical applications, two forms. The first is sealed radioactive sources. These are very small devices, things like a pencil in size, but typically extremely radioactive. Extremely high quantities of radionuclide are concentrated in these pencils. So the radiation is the level of radiation, gamma radiation, beta radiation, alpha radiation is extremely really high. The hazard is extremely high. And unsealed sources, not such high level of radiation, but they are not closed in a capsule. They are unsealed. So they can be dispersible. They can be in a solution, in liquid form, and gaseous form, typically combined with the chemicals. And here there is a specific safety guide published recently in 2019 by the agency, which I participated in developing of this guide. They started to develop it almost 20 years ago, 15 years ago, very, very long time. So at that time, I was invited as an expert, and I worked in the agency for 8 years. Nowadays, I left the agency. So after I left, they published it as a guide, and really you can find advices and based on experience, what to do with radioactive materials from the medicine industry and research, so including medicine. Then the material, which is waste, can be liquid, can be solid, can be gaseous, and then the liquids we can subdivide, can be water solutions, we say aqueous waste, or can be organic solutions. We say that this is organic radioactive waste. And then we can divide the waste into combustible and non-combustible. For the solid, we can say compactable, non-compactable. So all kind of subdivisions can be. But the major, it is gas, it is liquid, it is solid, is extremely important for the waste. So we start with the aqueous, because this is largest stream of the waste produced from the use of nuclear energy in the medicine. So it is produced also at radioisotope production facilities. So let's say a research reactor is producing some certain radionuclides, like maybe technetium-99 it is needed in medicine, or another radionuclide, and then there is produced some waste. So one of the waste stream, it is aqueous, some water solutions, these unneeded contaminants which are radioactive. So solutions typically are of small volume, but we have radionuclides there as contaminants, so we say impurities. So the content is really small, but because of radiation which is coming from this very small amount chemically, let's say, so micrograms and so on, can be nanograms, but nevertheless, the radioactivity is used also for the labeling purpose, because chemically is very, very difficult to find the content of some impurities. If these impurities are radioactive, they signal about them. They emit radiation, and this is labeling. Yes, so we can add an isotope to the stable material, and this is kind of labeling. In hospitals, the types of these liquids depend on techniques that are used for therapy, for diagnosis, and most of radionuclides which are used for diagnosis are really very short-lived. So half-lives are even less than 10 days. So then imagine we need to collect this waste, keep it somewhere, and let's say in a month or in a couple of months, they're gone. They decay. Liquid organics. This is some pump oil, some lubricating oil, some hydraulic fluids, scintillation solutions from laboratories, solvents from research, and generically, if you compare this stream of liquid waste compared with the aqueous, it's much smaller in the volume. So it's really very, very small. Even generically, by the nuclear industry is also producing organic liquids. But the volume of organic liquids waste, it's much smaller if you compare it with the volume of aqueous. So water solutions with suspended particles, something of everything which is based on water. Then we go to the solid. So this is, if you look to the medical and research laboratories, these are typically also the waste which can, so they are combustible. So some tissues, some paper, some towels, swabs, cardboard, some plastic, some the gloves, protective clothing which is used, it is vulnerable. They can be incinerated. So some nowadays a lot of masks, they are non-radioactive from COVID, but also to protect the lung and so on. In biological research, so these are the materials that typically can be burned, so they are combustible. If you speak about non-combustible, these are glassware, scrap metal, waste from the decommissioning of facilities where radionuclides were used. So these are solid. Then for medical, also gaseous, not just for nuclear fuel cycle, but also in medical applications. So first of all, can be airborne. So these are aerosols. But there are specific medical applications when some radioactive gases, like you see here, examples, xenon, krypton, it can be even Natrium-99, short-lived positron emitters are used, you see here fluorine and carbon-11. And this is to look how the lung of the patient is ventilated, and again to identify places that need real treatment, I don't know, maybe surgery and so on and so on. So everything can be visualized, and then the patient properly treated with the minimal risks to him compared with this when maybe there is no other method at all to identify where is the place of sickness. And now I'm coming to the most dangerous stream from medicine. Really, this is something like high-level waste in nuclear fuel cycle, or like spent nuclear fuel in the nuclear fuel cycle. This is disused sealed radioactive sources. You know, in 1986, Chernobyl catastrophe occurred. And a little bit later in Brazil, it was also a not global, but a big catastrophe with high consequences. When a source which contains cesium-137 in the city of Goiânia in Brazil, someone found it, and then about 4 people they died very, very soon after being in contact with the sources. Many patients were treated, and thousands of cubic meters of contaminated soil was collected there. So in the newspaper, this was called the most significant after Chernobyl catastrophe event in the world even. So many unfortunate examples are present, not such catastrophic like that, but you know, these small pencils that from outside look like very safe, nothing serious to look at, they are a little bit warm and so on, but they are extremely dangerous because of radiation which is emitted from them. So the activities, it's in a wide range, and by volume you can neglect them. This is extremely small volume compared with the volume of all kind of other waste, but the radiation coming from these sources is extremely high. So this time these sources cannot provide necessary levels of use. So if you have a gamma knife, then if due to the decay, the intensity is not so high, you need longer time of treatment, and this is not affordable, not possible. So because of that, we say that the sealed radioactive source becomes disused. It's not needed. It's like waste. And then care should be about how to deal with these sources, and not only cobalt-60, cesium-137, a range of radionuclides are used. So they are used not only in medicine, they are used by the industry, these sources, for all kinds of devices. We are coming in such a way with these materials that previously they are just described to you, to the radioactive waste management, to the section that we need to manage this waste. And this is not simple waste, this is radioactive waste or nuclear waste. And the portion of this waste is coming from the use of radioactivity in medicine, and it's radiopharmaceutical waste. So pharmaceutical, these radionuclides attached to them. Generic information. The radioactive waste management, it's a national responsibility. We have an international organization which is IAEA, and this organization is only helping nations. Responsibility of the management of radioactive waste, it's on governments of countries. It's a national responsibility. And the nation can ask agency. It has no resources, no information, no different kind of even regulations how to do. Can ask IAEA for assistance. But the management itself, it's a national responsibility, and regulations must be national, so everything is into the national. Only advices, only assistance is coming from IAEA. Then it's some key information that we need to care of the management of radioactive waste. Otherwise, there is no trust of generic public into the safety of nuclear sector, including even nuclear power plants and so on and so on. And here it's necessary to develop integrated waste strategy and so on. So when we come to the management of radioactive waste, we have two types of activities. The first one, administrative activities. Administrative activities, they are typically regulated by the management systems. So you see here waste management planning, establishment of inventory, and all other things, among which is technology selection, so not application of technology, just selection, cost estimation, licensing, waste management operation, that goes, they are also on the management systems. And then we have the real operation, real things when we go to the waste, take the waste, process it, finally transport it, finally dispose it off, operational activities. And here in radioactive waste management, we have two types of activities. Pre-disposal, so we prepare the waste for disposal, and disposal. And in pre-disposal, we have a large range of activities. See here, processing. And processing means pre-treatment, treatment, conditioning. And under them, you see here other things that are, so these are operational activities. When we manage something which is nuclear, something which is emitting nuclear radiation, something which is radioactive, we got here useful materials, and this part of the picture, and waste. This is radioactive or nuclear waste. So if the waste is below clearance levels, it is clear. Some discharges are allowed, but if they are above the clearance levels, we go to the activity which is under regulated disposal, and we need to apply first pre-disposal to prepare the material for storage initially, transportation, and finally disposal. So I came to the point when I prepared here a special slide. I am starting it. So you got 5 minutes to have a breath from my voice, from my slides. Think a little bit, have a little bit relaxation, and then I'll go to the second part. So just 5 minutes. So, dear participants, let me continue the lecture. So, management of radioactive waste. And there are roadmaps. How typically do we proceed when we manage radioactive waste from the point of view of operational activities? What do we do? So this is a scheme, not to bore you of describing everything, but typically it's divided into the stream, and then with each stream there is a good IAEA document. I participated again in publishing it. You see here, it's about the policies and strategies for radioactive waste management. It's something which is widely used by regulatory authorities, by the agencies, because all kind of hints, recommendations how to develop policy, how to develop a strategy of radioactive waste management, and even how to go to some detailed recommendations are there in this IAEA publication. And again, it's the cover of this book when you can find all kind of operational things that we do with the radioactive waste. So when we speak about the radioactive waste, this is something which, let's say, lives very long. It's a life cycle of nuclear waste. And it is here described in this slide, because things are starting with the place where the waste is generated, and then we need to collect this waste, maybe to be absolutely necessary to characterize it, maybe to segregate into some streams. So that part, it is called pre-treatment. So it's actually, we are just identifying what to do with the waste, not really treating it. But then we go to the stage which is called treatment of the radioactive waste, when we are trying to reduce the volume, to eliminate some of the hazards. So let's say if it is burnable, it can catch fire. Then we use an incinerator and transform everything into oxide forms, like that. Then there is a conditioning. The conditioning produces packages. So for transportation, for the storage, finally for the disposal, we use packages with radioactive waste. Something which from outside it's a container, but is a package. Inside of this container there are other things, and the waste, it is there in the container in a form which it's called in our part, it's called waste form. The radionuclides and the waste form actually are. So conditioning is producing a package. Then we go to the storage. Necessary to the disposal most often is not available, and even in the nearest future is not yet. Let's say if we speak about the high level waste, transportation, and then finally we will reach the very final point, which is called disposal. And we understand that due to the decay of radionuclides, the natural decay, radioactivity, it is there present. It's not the end of the life of radioactive waste. They still are alive there in the disposal site, and we should be sure that the radionuclides are not mobilized and will not return back to the biosphere and will not harm the environment and us, the humans. So this is the description, and we are starting with the waste characterization. Waste characterization, it's important everywhere. And it should start at the very beginning when we are dealing with the raw waste, because we need to decide what processing is required. Maybe this is very short-lived waste and just store it, or maybe we are lucky and this is exempt waste and just clear it and nothing to do from the point of view of radioactivity with this material. At interim stage, to ensure that meet the requirements for processing. If you have some radioactive waste that it's intended can be incinerated, we need to be sure that the content of, let's say, transuranic alpha radionuclides is not too high. Otherwise, the incinerator will produce gaseous waste and the gas purification system will not cope. And then we have, in United Kingdom, let's say in Sellafield, we have the waste acceptance criteria for incineration. Not all the waste are accepted to incineration. And all facilities actually have waste acceptance criteria. So we need, at these interim stages, characterization to know what kind of radioactivity, how much of this radioactivity is here. And then conditioned waste. Conditioned waste, it is stored. And finally, it is transported to the disposal site. And all disposal sites, they have the documents which are called waste acceptance criteria. And waste acceptance criteria, a range of parameters, including dose rate, including the weight, of course, sizes, properties of the waste packages. And if the package which is brought for the disposal, it's not in compliance with waste acceptance criteria, is returned, remanufacture it. Do it in such a way that we will be able at the disposal facility to accept it. So we need everywhere characterizations of some pictures here that about the measurements and so on. And again, I'm coming to the roadmap. So there are here in my slides two roadmaps. So the one is for solid, another is for liquids. And here, all kind of, here things are done. We need to know, maybe this is exempt waste, or maybe it's very short-lived, or maybe it's very low level, maybe low level, maybe intermediate, and maybe high level waste. And then we will get to different endpoints. And in order to know what we are dealing with, we do characterization. So characterization should start as soon as possible, And characterization does not necessarily mean measurements. It may be that characterization can be done based on available information. If this is a source of radiation, that is this pencil that was used in a gamma knife, we have the passport of this device. We know for sure what kind of radionuclide, what was initial radioactivity, what is the time of use of it. We just calculate and we know exactly what is here. So in this case, it's just to check, to ensure, so just to verify, only verification. Or if it is a legacy waste taken from a vault somewhere in Sellafield, nobody characterized it, there is no even documentation of it, we need to take samples and to do very difficult things on characterization. And we do that both for solid dose and even for the gaseous, of course, radioactive waste. And again, it's many things. And characterization, it's things that we start with, but in reality, everywhere on the way, on the roadmap, we do characterization. And there is a special roadmap for the disused sealed radioactive sources. So this kind of picture which is here, it's let's say focus on it because you are interested in the radiopharmaceuticals and medical use of nuclear energy, right? So these use sealed radioactive sources. So we have a source which is considered as disused, but maybe that it is so good condition that here is not good, but maybe it's usable. Maybe another user it's going to use it and can be redirected, and instead of going to this stuff which will end with the disposal, we will usable source, return to supplier, transfer to other user, store for future use. Don't be in a hurry and dispose it off, because there's a lot of activity there concentrated and can be somewhere very much needed, this material, if it is a good condition, of course, if it is not leaking and other things. And it's so more or less useful case, so useful material. But this used source which nobody needs it, then is a waste. What to do with this used source which is not needed? This used sealed radioactive source which is like a waste. There are situations when it's leaking, and when it's leaking, it can create disasters because it's contaminating everything around which is in contact with this material, with this source. So then we need to do packaging and then to move to other step. For non-leaking sources, we are going to characterization for disposal. And here, it's not just needed to know, the activity, the dose rate, and so on and so on. It's very important to know the total life needed, the total time needed for the decay to the clearance level. And then we will understand if it is very short-lived, we are lucky. If it is short-lived, can be also. If it is long-lived, we will need to go to somewhere. If the question about thousands and thousands of years, very deep on the ground. So that's the case most often of intermediate or even deep disposal. You see, that is the case. And you see here the case storage for very short-lived, conditioning packages. The geological disposal are not nowadays available anywhere. Maybe the RIP repository in the United States, in Colorado. This is in reality a geological disposal. It is called for transuranic, but it's a geological disposal. But I cannot name any other place in the world that is geological disposal. So because of that, you see here long-term storage until it will be available. the part which is called predisposal management. So I'll go very briefly because this is also the case of non-radiopharmaceutical. In radiopharmaceutical waste, most often this is very short-lived waste. Apart from this huge lucrative sources, that's why I'm focusing your attention on this stream of the waste. This is a real, very hazardous waste, and then it goes like in this part, other nuclear waste. So predisposal. We are preparing the waste for disposal, and then you see here we got radioactive waste, pre-treatment, treatment, conditioning, storage, and only then we will get to the disposal. You see here characterization, and these activities are called processing altogether. And the principal approach in predisposal is delay decay. Sometimes this is delay decay not very long, we can afford it, sometimes not. Then we concentrate and contain, and in specific cases, imagine a small country which maybe has produced 1 liter or 100 liters or 1 dram of the waste, which is contaminated soil or something like that. In this case, the common sense works everywhere. And in this case, for this 1 liter of not very radioactive material, which is above the clearance level, it is allowed and it's reasonable to dilute and disperse. And because in reality, you must justify that. But if this is in a position and situation that is justifiable, then dilute and disperse. It's also, or for low probability scenario, noble gases. Chemically, they do not interact with anything. So they are decaying without harming anything in the environment and humans. Processing means all kind of activities starting with treatment, conditioning, storage. So pre-treatment, it is just when you collect the waste. Just you collect the waste. In a treatment, there are different technologies. So here, compaction, when the force of compactor is not very high, so maybe 50 tons, maybe 10 tons, like that. If you go to 1,000 tons, we call this compaction super compaction. Then we got incineration for burnable waste. For the metals, metal melting, pyrolysis can be as well. For the liquids, typically ion exchange, filtration, precipitation, evaporation, these are the main methods. Then conditioning is producing packages, and you see here that sometimes we use immobilization, and then we got storage. So altogether, this part before the storage is called processing. And then the explanation of all these stages. So what is in the pretreatment? This is the proper definition of pretreatment, and the picture just explained that this is collection, segregation to the streams, size reduction, chemical adjustment, and decontamination is by definition also pretreatment operation. Typically, the waste is the same after pretreatment, except for decontamination. So nothing happens with the total amount of the waste. If you cut in two parts a piece which is radioactive waste, bar, something like that, is the same waste which is now represented by two smaller pieces, so that you can put them into a container. So because of that, such operation is not treatment. This is pre-treatment, previous treatment. The objectives of pretreatment, so again in line with the previous cycle, and the examples. So when we collect, we prepare this drum with the waste there, or maybe we sort using the glove box. So this is from the national project that I was the scientific officer. It was in Caucasus region in Georgia. So that we cut larger size ducts, pipes into smaller pieces. So that was pretreatment. Decontamination, by definition, IAEA decided to term it as a part of pretreatment. And yes, we can after decontamination, maybe even reuse some materials, some tools, and so on and so on. In some cases, the spots of radioactivity in some places which are very high, decrease them, and the total amount of the waste by decontamination can be even increased, because when we remove the activity from here to where? Maybe to a washing liquid, then the total amount, it is higher. We produce even some additional waste. Because of that, decontamination is considered not real treatment. It is pre-treatment. And if you go to the treatment, the objectives are different. We intend by using treatment to reduce the volume. So this is again the definition of what is treatment. we need to remove activity from the waste itself. So if you incinerate the waste, it was a large amount. The final waste is the ash. Practically all activity is concentrated now only in the ash, and we reduce the volume and remove the activity from the bulk of the waste. And change of composition. Instead of dealing with the burnable, higher hazardous material, we got here oxides, which is not fire hazardous. Then for different streams, there are different recommendations. They are given by in this IAEA document. This is about the technical solutions of you see here for liquids, for a solid radioactive waste, and this is the table for gaseous. And for gases, there is a handbook published by agency. These two documents, I prepared them and I published during my term, 8-year terms. I was staff member of IAEA in Vienna. So I invited experts that I know. So they were working in technical meetings in preparing these books. And nowadays, these are technical recommendations where the reliable, the proven technologies are recommended to be used in the context. Conditioning is producing, so this is the definition, is producing gases. In some cases, in conditioning, we need immobilization. So if you have liquid radioactive waste, we need to transform this waste from the liquid into a solid, so to immobilize the waste, which is in a mobile form. In cases when we have some solid materials, we can put just them into a container, and this is also conditioning. We will add some backfilling material, maybe it will be cement grout, but this is not real immobilization like for the liquids. And we use packaging, we use overpacking in conditioning. Then this is immobilization, so it's solidification of these liquids, it's embedding of some solids into a cement, let's say, into a solid material. It's encapsulation like we do when we use bituminization. So salt particles are covered by the bitumen film, and everything is the body of the bitumen. And the same it is done actually in cementation. There are many materials that are used for immobilization, and there are dedicated publications. This is a book that I prepared. So cement, bitumen, polymers, glasses, optimal materials for high-level waste, let's say, and ceramics, which are under investigation. And actually, there is a correlation in between the materials which are used for immobilization and classes of radioactive waste. And this is illustrated by this picture, this slide. So if we speak about exempt waste, this is not our business. Very low level waste, it is left as waste. Maybe some bags are used, some very simple packages, but nothing else. So that waste goes, it's a little bit above the exemption levels here on this plot, and it goes as is. The activity is not high. We are a little bit above the clearance levels. There is not much hazard from this material. It can go to industrial sites of the disposal of industrial waste. There may be to municipal sites, and there is not a real application of immobilizing materials for this waste, for very low level waste. When we come to the low level waste, the hazard is significant. We need insulation of this waste in near surface repositories for several hundred years. Otherwise, it's hazardous. And in this case, cements are the basic materials, cements. But of course, not only. So the bitumen, the polymers which are used, there are containers, there are even such containers which are called high integrity containers. So high density polymer, polyethylene, it is used to manufacture these containers, and they are actually used even for you see here high integrity containers for intermediate level waste. The same situation is for intermediate level waste, which requires longer times, cannot be disposed of at near surface, but can go to intermediate depths. And you see here glasses appear. Sometimes glasses are used even for low level waste, and we have such examples from the United States. In Russian Federation, they developed vitrification technology for operational waste from nuclear power plants. But basically, they appear here, so they when the hazard is high, it is advisable to use glass as the material which immobilizes the radionuclides. And if you go to the high level waste, most of materials disappear here. For immobilization, we need glasses. We can use ceramics, metal containers. we need really very durable materials in this case, because the concentration is so high of long-lived radionuclides, maybe short-lived, but their concentration is extremely high, that the total time needed is 100,000 of years, maybe millions of years. And during such long times, if the radionuclides will be able to migrate from the place of the disposal, if the source term there will be such that many radionuclides can be involved in migration, then a part of them can reach the biosphere, can reach the humans. And in order to minimize the risk associated with that, very durable material shall be used, and actually glasses are optimal materials. You heard about this is mainly nowadays borosilicate glasses, but of course not only. Phosphate glasses are used for many decades in the Russian Federation. They were used for a certain period in Europe, also in Belgium, with Germany. But nowadays, only Russia, Russian Federation still uses phosphate glasses, and all other countries, they are using borosilicate glasses, which are a little superior. It doesn't mean phosphate glasses are not good for immobilization, but fairly speaking, borosilicate glasses are more durable, more resistant against corrosion and all kinds of defects, and most of users prefer to use borosilicate glasses for immobilization. Then we go after immobilization to the packages, and here just some photographs, all kinds of containers that are used. Drums, typically 200-liter drums are used for packaging. Can be for metal waste, metallic ingots, ISO containers. If we speak about low-level waste, which is disposed of, then we see very large ISO containers that are suitable for the initial primary drums are there, and then everything is filled with the grout there, and then these are very good packages that can be transported from one side to another and disposed of in near surface repository. So this is, but can be half ISO container, 1/3 of ISO container. So we speak about some boxes. Concrete is a really very durable material, so then that can be in cylindrical shaped containers, rectangular containers with different volumes that are used for packagings and even open packing. So imagine if the content of radioactivity is high, then the dose rate is also high in the container, and particularly in the transportation, in overpacking. If you have a transport unit with a good shielding and the put the container inside just in order to shield the radiation. So we call this container as overpack. It is used just to protect. There are transport regulations when there are the certain regulation about the dose rates from the container during the transportation. The same can be in the storage facility. So because of that overpacking, and overpacking, it is often used for a legacy waste. So in the past, when there were other regulations, many packages were manufactured based on previous instructions and regulatory advices. Nowadays, they do not comply. Then there is overpacking. Rather than destroying everything and immobilizing the old, let's say, 200-liter drum or 100-liter drum, it is put inside of another larger drum. The gaps are filled with the grout, and we have overpack, which provides compliance with current and makes the package more reliable to retain the radionuclides and to be accepted for the storage, transportation, and disposal. So we call that overpacking. And we are coming in the life cycle of radioactive waste to the stage which is called storage. Storage is temporary, but for the radioactive waste, storage can be quite long. Because in many cases, the storage is until the disposal facility will be available, and is not available, and is not even available in a foreseeable future. This is the case, let's say, of long-lived waste, high-level waste, where the question is about deep geological disposal. And that requires many tens and tens of years to get it available, licensed, and available to accept the packages. And then we move to the long and even very long-term storage. And the question is, can go beyond even 100 years. And this is the place where the United Kingdom came to. So the storage facility is for over 100 years. And this is the case, let's say, in North Holland, so in Netherlands. And it was found that for such extended periods of time, it's not an easy thing to do. So you may imagine that put it in the storage, just wait. But if it stays in the storage for a long time, it corrodes. And let's say in the United Kingdom, we are living on an island. And the vapors which are circulating, we are breathing these vapors from the sea and so on. They contain fluorides, different kinds of sulfates and so on, which attack the metals, which corrode the materials, and not only we, the same in the Netherlands. So if you go, and in Austria, by the way, that I was a staff member of IAEA. So if you go to the very extended, so if you speak about 50, 100 years of storage, you need special conditions for storage. And the conditions are such that we control the moisture, the temperature during the storage of radioactive waste. And the conditions in the storage are so good, that it's very costly, by the way, that in Netherlands, there are sections of the storage facility where they preserve their precious pieces of art. Some old pictures that need very stable conditions of the storage, and they are. And you imagine that is not for free, because to condition the air and to keep it there during hundreds of years, it's something very, very costly. So in reality, very long-term storage is extremely costly and is not, so it's not cheap. It's not much cheaper than the disposal. So everywhere, agency and the Nuclear Energy Agency, International Atomic Energy Agency, they recommend final endpoint node storage. This must be disposal. So only that is the final point when they can assure that that is not something which is transferred to the next generation. So it's in line with the principles of radioactive waste management. Okay, so that's the definition. What about the storage and the endpoint? Disposal. So it is the emplacement of the waste in an appropriate facility without the intention of retrieval. So there is no intention that in the future we will take back the waste. So that's the definition of the disposal. But in some countries, and example is France, the population thinks that who knows, maybe in the future we will become so smart that we will decide to retrieve the waste from there. So because of that, the reversibility in some places it is still in place. So we dispose of, we have no intent to retrieve the waste back from there. But if that will be discovered later on, let's make the design in such a way of the disposal that this technically will be nevertheless be paused. But that is only in some cases. When this reversibility it is still in the design. So anyway, the disposal this is not storage. The storage at the end of storage period, we must be able to have a good quality package which is immediately available for the transportation and is immediately accepted for disposal. So it is not corroded, it's not decomposed, and so on and so on. There are for the disposal different type of the facilities. So near surface disposal facilities, these are intended for low-level waste. Without and with engineered barrier systems additional. So in some desert areas, we can afford to dispose without additional engineered barrier system. In the places like in Russia, in the United Kingdom, we need additional barriers which are engineered in order to protect the packages for their premature decomposition and the action of atmospheric precipitates and so on. Boreholes and cavities are for intermediate depths good for intermediate level waste. And then we go to geological disposal that also can be boreholes. And by the way, their boreholes are really a kind of a variant that can compete with the mine depositories because they are several times cheaper. And several times for geological disposal means saving of billions of dollars or pounds. So they are extremely costly. So there are designs of boreholes that can be turned into a suitable geological facility. So these are called horizontal boreholes. And this is an overview on different types of borehole disposal. The plant, there is interest in the Russian Federation, in the United States of America, and several European countries on a horizontal boreholes, these things that are shown here schematically. And we planned with them even a joint workshop. It did not happen, but nevertheless, it's something that because it's much saving resources on building such. I'm informing you because maybe in your country you will be aware that there are much cheaper disposal options for radioactive waste. So conclusion. So the radioactive waste, including radiopharmaceutical waste management system, it is well developed, ensures that any waste generated is safely and efficiently managed from the point of generation through to disposal. So dear participants, exactly in time, maybe a couple of minutes for some questions to me, points of discussion. So I will stop sharing, and please, if you want and have anything.
Thank you very much, Professor Razvan. Any questions? Yeah.
First of all, thank you, Professor, for your nice presentation. I am interested in asking some questions on typical management operations for liquid radioactive waste. On page 13, maybe 30, I mean, you have indicated different operations for liquid radioactive waste. And when it comes to especially the high level waste, the options that we have is immobilization and finally the disposal. My question is now, do we have don't we use any pre-treatment or treatment options before immobilization or storage for high-level liquid waste, which is radioactive?
I see. Yeah. Thank you that you paid attention even to that. So yeah, thank you for the question. I really appreciate that. The case of high-level waste, the same like spent nuclear fuel, it's in practice, all stream, it's a little bit specific. So the stream of high-level waste is specific from the point of view that radioactivity is so high. The radioactivity is so high that they generate even heat, so much heat that the tanks for high-level waste even need cooling. So there is a mixer there, some additives, chemical additives there, and then cooling. Otherwise, they are overheated due to the radiation. And because of so high radioactivity there is no reason further to increase the concentration of radionuclides and to try to save an additional volume and to make the volume even smaller, because already the activity is so high that produces problems. And because of that, of course, from the liquid radioactive waste, which is high-level waste, the water is evaporated. So get rid of the water. Then the remnant salts are decomposed. We call this process calcination. And then the oxides, to these oxides are added additional components, which finally will produce from this high-level waste a good material. And this good material is a glass. It's a borosilicate glass. So we need to add some silica, so silicon oxide. We need some boron oxide to get a good quality borosilicate glass. Maybe other components, like we add a little bit lithium oxide, which helps to get a good quality glass. Many components are already in the high-level waste, which allows to obtain a very good quality glass. But anyway, to reply to your question that you put, there is no need for the liquid high-level waste to treat it further, because the main treatment objective is to reduce the volume. and the volume is already reduced in such a way, concentration is so high that we have very high radiation fields, very high amount of heat generated, and further treatment will cause only troubles and problems. And in principle, at the beginning of the era of developing ceramics, you heard maybe about the thin rock and these things. One of the arguments from ceramic was that let's further concentrate the radionuclides in order even further to increase the volume. But this is not reasonable to do, and nowadays this is not an argument from the ceramic specialist, because it's real. It's understood that is already enough high concentration that it's difficult to work with, and further increase of concentration may cause big problem nowadays and even in the future.
Thank you. Any more questions?
Thank you. Thank you for the presentation. I would like to ask, like, for me, I'm doing the research work. My research work topic is about the nuclear waste treatment, but using ADS, accelerator driven system. What's the effectiveness of that technique to the nuclear waste treatment or transmutation? Thank you.
Yeah. Dear participants of this school, you are getting overviews. So I was asked to give an overview, and in order to do so, I couldn't note even a small fraction of things that are under investigation. One of the methods that is under very significant and very important research is transmutation. When we are coming to the point of long-lived waste, this Neptunium-237, all these radionuclides that actinides, they require very, very long times of the storage. One of the approach, scientifically justified, is to take these radionuclides to bombard them by using accelerators, as you are doing the research, or maybe to process them in a fast reactors where you have very intense neutron fields by neutrons that can transmute the radionuclides and transform them into a short-lived. And the advantage of this technology is such that we are not, first of all, geological disposal is extremely expensive. This is one. Second, so you pay for each cubic meters, you can go even to millions of dollars per cubic meter. It's very, very expensive. In addition to that, the confidence in all our models, if you go to such extended times, is not very high. We don't know really what's happened with the materials that are very radioactive and are for such long time. And if you will move to the times of 100 years, the science gives very confident replies what's happening with these materials. So we will make everything much cheaper. But the research that you topic that you work on and many other organizations, this is a question of scientific research. It's nowadays it's too early to say even it's a feasible technology will appear or not a feasible technology of using this method. At the moment, it's like many other investigations. It's a question for the science. At the moment, it is seen as an extremely expensive, generating all kinds of other radionuclides and producing all kinds of other problems. And no sites, no laboratories that are at the stage of moving from fundamental research to the real application at the moment. But the research, of course, should be done because this is an extremely interesting solution. It is something that, in addition to the nuclear waste management, brings other results. So, as a research, it's something that is done and shall be done, but it's not a point of technology yet. Will be in the future, perhaps, and there are dedicated reports on that with more details that, in simple words, I just said to you.
Okay, thank you. One more question. There is a question online in Zoom. So in case we have a high concentrated solution, dilution can be an option or not?
So this is the question. Once again, be careful. I tried to explain carefully this to you. So this is a very specific case. Generically, the answer is no. No, and that's all. But only generically. In specific cases, when the total amount and concentration are small, in these specific cases, this is an option. And this is common reason. In the case when, you know, a nation, let's say, and there are small nations, I don't know, Montenegro in Europe, it's less, it's half a million, 600,000 populations only. Imagine that the activity they do are not very, very large. Maybe a small population does a lot, but nevertheless, if the total amount of radioactive waste is very small, then for a small amount of waste, let's say you have even 1 cubic meter, you will not develop a vitrification plant which costs millions and millions of dollars. You cannot do at all that. In this case, one of the solution is this dilution and dispersion. And this is specified in the basic safety standard. By more detailed words and simple words I'm explaining to you. And these specific cases, this is an option, even for normal, naturally occurring radioactive materials. So these are radionuclides that already are present in the nature, some thorium, some uranium. And if this amount is not very high, you are a little bit above the clearance level, and you can dilute a little bit the soil, which appeared in oil production and so on. You can maybe mix it with the non-contaminated soil below the clearance level, and is justified that there is no real harm from that, then this is a possible solution. But generically not. Only in specific cases, and should consult the recommendations from the IAEA, which are positive, and of course approved everything through national authorities. So if you are in a laboratory, if you work with radioactive materials, you are in a position to do that, but don't do that until you will not get permission from a regulator that cares about that. And officially, there needs you through clearance procedure to do that.
Okay, thank you. Any more questions? No? Okay, if not, thank you again.
Okay, thank you.
So now we have a break, lunch break, and we have these papers.
Все, начинаем. So, dear colleagues, have a good day. So, my name is Evgeny Menshikov, and I'd like to tell you about intellectual property. So, today we will discuss why it's important, what it is, and why it's useful to know about it. So, let's start tell about general information about intellectual property. So there are different types of intellectual property like patents, utility model, copyrights, registered designs, and so on and so on. So let's briefly discuss about it. So patents usually protect any technical inventions, any technical solutions. It's protect any technical solutions, like machines or different methods. So further we will discuss it more in details. So utility models, it's also protect any machines, any inventions. So, but it's a more simpler way to protect your inventions than copyright. It's protect any artistic works like art, draw, any literature, and also some patenting code, any coding in for information technology, also covered by copyright. Then trademarks protect trademarks protect some pictures or some words which distinctive you, like identification picture from other competitors, or distinctive you on a market, like distinctive you like a product or any service. So registered designs, it's all about viewer of your product and some kind of shape of your product, like a shape of Coca-Cola bottle, you can protect by registered designs. And also trade secrets, it's a way of IP protection. Any ideas or any kind of information which can has any commercial value because of its trade. So actually there are a lot of IP objects in one product. For example, if we take a cell phone, we can find a lot of IP rights, a lot of IP projects, a lot of trademarks, objects of copyright like a software, user manuals, ringtones, images, and so on. Of course, like a cell phone is like a technical device, has a lot of patents and utility models for data processing methods, operating system, operation, and any interface, and so on. Of course, there are a lot of registered designs. Yes, it's like a shape, it's like a view of any icons, position and shape of the screen, arrangement of the buttons and their shape. And also cell phone has a trade secrets also, because some kind of secrets of production, any elements or any parts of it, or programming code, it's protected like a trade secrets. So why the intellectual property is important? There are some answers for that question. The first is IP is essential business assets in knowledge economy. We can give some examples like Google or Facebook company, which a lot of a big part, a huge part of their value its value of intellectual property. Also, Sandvik or RM Holdings, yeah, like innovative companies, has a lot of employees and production volume, and also these companies has a huge huge patent pool, yeah, and IP pool. So anyway, for big companies, the huge patent pools, it's a way to make big advantages in the market and have the most advantages in the competitive race. The second is for IP protects small innovative firms. So I think all of us hear about innovative Gore-Tex textile type. Yeah, it's a small company which has a patent for Gore material. This is a membrane material which keep you dry and keep you from the wind. And all business of Gore company, it's based on this patent, and it's allowed to this company produce a huge amount of textile and make big money for production or for license their patent. The third importance is IP needed to enable release into the public. For example, if we look at the example of Linux, yeah, it's open source, but it's open source which distribute according to GPL, General Public License. And the idea of this license that you have Linux, it's open code, and you can take it, you can install, or you can approve it. And if you take any open code according to GPL license, you need all advantages, all your improvements, also distribute according to GPL license. It means that all improvements is also open. It's also open source. On the other hand, we can look at the Creative Commons license. This is common license works mostly with copyright objects like texts, images, any draw, music, and so on. And actually, you can make just select conditions for this for your object and for your necessity for type of license do you need, because Creative Commons license, it's like a constructor, and you can combine any options which you need, and all these options is detailedly described in this CCL license. Next, advantages of the next importance of intellectual property. IP helps guarantee standards for public benefit by means of license or trademarks. Yeah, for also you can register a trademark and you make any kind of franchise, or you can make any public benefit for example, for fair trade or forest council and so on. So usually, if we look at the market, on each market there are a lot of competitors. Yeah, and all there try to have benefit from their efforts. They can offer similar or identical products at a cheaper price, but not all competitors are innovators. Yeah, innovators, this is guys which make something new, make something innovate, something that there were nowhere before. And Also, they make significant investments in the developing new products. Okay, but if you make an investment in new product, you need the mechanism which can you renew or back your money for your innovative products, and you need the mechanism which prohibit other competitors use your technology, and IP system gives this opportunity because rights of the use inventions, designs, brands, and also IP objects. If you honor the IP object, you can allow or prohibit other competitors use your intellectual property. So let's discuss each kind of intellectual property more detail. And the first I want to discuss is the patents, because patents is the main intellectual property type for innovation, for innovative entrepreneurs, for technical improvements, and so on. So, the first of all, that the patent, it's like patent, it's the document which protect your technical solution. So you have the exclusive right to prevent others from making or using or offering for sale products which your patent cover, and you can protect, and you can protect your invention, and nobody can infringe the patent. So actually, patent it has country location. For example, if you protect your invention on the one country and somebody use your patent on the other country, he's not infringes your patent, because patent has localization in the country which it works. So if you wanted to use or produce or make your production in some countries, you need the patents on in each country you want to use your invention. The second limitation of the patent is the time. The time limitation is 20 years. So after 20 years, patent stop protect your invention, and it starts the public invention, and anybody can use it. So what exactly we can patent it? So we can protect any processes, methods, uses, or can protect any chemical substances or pharmaceuticals, or any products, devices, or systems. So there are three criteria for invention to be patented. So the first, your invention should be new, absolutely new to the world. It means that there are no any available public descriptions or disclosures your invention. The second is inventive. So if you want to patent your idea, it should be inventive. It means it should not be obvious solution for this area. And the third criteria is industrial application. It means that your invention, your idea, it's shouldn't contradict with any nature rules, physics, chemistry, and so on. If your idea, if your invention or technical solution is your idea is new, has not obvious, and has industrial application, you can patent it. So actually, the IP, intellectual property IP, you can use by different way. So the first is you can encourage technological innovation. Yeah, we told about it. The second, you can promote competition and investment. And actually, if you start the dialogue with the investment, usually he asks about your idea, about IP, and about the team, because it's the most important things in any project. Then also IP and patent system is promote the technology transfer. And the idea of technology transfer is that if you have a patent, if you have a technology, you can not directly produce the final product. You can give the right, give the possibility, use your invention, use your patent for any payment from the other side. So actually patents, it's like a social contract. Yeah, we have already told about competitions and competitors. So patents, it's like a social contract. On the one hand, you're like an inventor, disclose your invention and detailedly described how it works, any composition and what it consists. And on the other hand, you get the exclusivity, the exclusive right to use your invention, which you already described in public. Just you and you like a start monopoly for these 20 years. After 20 years, of course, your invention start be public for everybody. Okay. So I have already told, but it's useful to repeat that the rights conferred by patents. The first, you have right to prevent others from making, using, offering for sale, selling, and importing infringing products in your country where the patent was granted. Take your attention that in the country where the patent was granted. Yeah, if you wanna have the same rights in other country, you need to be to have patent in other country also. There is one exception. If somebody use your technology or your invention for non-commercial purpose, for like private use or for academic research, it's not infringement, you're right, and people use your invention for this non-commercial purpose. Yeah, for example, some these images I took from any base, and I don't need pay for it because we make it for academic research or and academic purpose, non-commercial. And then if you have a patent, if you granted a patent, and if you have any rights, you can you have a right to assign, sell, or license their rights. Yeah, license, we told about it. You can give your right for production or for making, for selling your product, and have some money for it. So the main point is that a main is a negative right. It means if you have a patent, you have right to prevent others from exploiting your inventions. But it's not enabling right. It means if you have a patent, it's not guaranteed that you can produce your invention. For example, if we look at this, look at the situation. The first patent, for example, cover protection like electric kettle, yes, and then you, like an invention, you make some improvement of electric kettle, and patent grant patent B. So patent B is your, yeah, like electric kettle with a ceramic heating element. So on the one hand, you can prohibit anybody to make electric kettle with a ceramic heating element. On the other hand, if you want to produce such kind of kettle, you need to have any right from this base patent, like electric kettle. It means owner of patent A, he can, for example, make electric kettle, but not like yours. But you can make electric kettle with a ceramic heating element, but if owner of patent A allow you to make it. So in usual situation, if you have some innovative product, you should check which patent are covered by your product and to give any permission or any right from these owners for production your innovative product. Okay, so what do patent documents look like? So the good news that the view of all patents is uniform for any countries, and the view is the same. And moreover, all things is numbered, and even if you don't know, for example, Chinese or any other language, you can understand where is inventors, or where is date of priority your patent, or where is description, and so on. But usually document has date of publication, date of filing, and date of application. So let's discuss about these dates. The first date of filing or date of application, it's a very important date because previously I told you about three principles and three conditions for patenting your technology. The first was new. So when the expert in patent office will examine your application, he will check all technical solutions which have been known before the date of application, date of filing. So date of filing is it's very important date. After 18 months after your application, it will be your application will be published, and date of publication it's a date when the patent office make public your application. Then this is application number, so technical classes of your invention, inventors, abstract, owners, and so on. So the main part of the patent, this is the claim. Claim or claims. This is the one sentence, but this sentence specify all your rights in a patent and all your rights according to this big paper. All other information in a patent, it's just like description and explanation of your idea which contain in claims. So all legal strength there is any claims. Okay, description of the patent contain some parts. The first is the prior art. It's all known before technical solutions, all known before inventions, before your application. Also, there is a drawback of prior art. There is a description of problem to be solved by your invention. For example, if we look at this invention like a sport tier port with a two spout. So prior art, this is T-sport with a one spout. Drawback of prior art, it's time consuming. We'd like to reduce the filling time for multiply spout, and the solution will be provide a second spout. And also in a description we write about advantages of our invention. So the advantages of this example is filling time is reduced. So we have already told that for invention to be patented, it must usually be new, inventive, and it should has industrial application. Means it's not, it shouldn't be contradict to any nature rules. So we can protect any products like chemical substances or devices, machines, systems, or any of this, or any processes like methods or uses or something else. So when we tell about new, so I have already told that date of filling it's very important. So when expert will check state of art, he will check all technical solutions before date of filling. The date of filling is also important if we decide what we should do first. For example, make an article or make a fill in the patent. And of course, the right way, the right order is the first you need to fill in your application and then make an article. Because if we publish article before and disclose our invention in article fully, expert will find it in a state of art, and our article will contradict to our feeling because of our feeling will not be new. So the right order, it's the first step. We will make the patent filling, and then we can make any public description of our invention. So this is a very important thing. Okay. So before filling application, we don't we shouldn't publish any articles, press release, conference, and so on. And also, we don't sell any products because selling products is also public activity which can disclose our invention sometimes. On the other hand, what we should do, if we give somebody, for example, investor or something like this, disclose our invention, yeah, we should sign non-disclosure agreement. It's a paper. It's a contract between two parts, which prohibit to make public any information which two parts share between them. Okay. Okay. There are some advantages and disadvantages of getting patents. Of course, if we tell about advantages, it's exclusive. You have exclusive right for investment and higher source of investment. You have a strong enforced legal right, and you can make sales or license. On the other hand, you have some disadvantages. The first is publicity of your patent application after 18 months after filing date. Yeah. So all your competitors will be know about your invention after 18 months. So it can be expensive, especially if you wanna protect your invention overseas. So for example, if you have any protection in United States, it will take around $5,000 around this. In Europe, it takes around 10,000 euros and something like this. So depends on the country. Granting a patent, it makes some time. It depends from country to country. Depends significantly. For example, for Russia, usual time for granting patents less than 1 year. For example, in States, it's usually around 5-6 years. In China, it's around 3-4 years, like this. So it depends. And usually, if you need to decide should we patent or not, you should answer for some questions. The first is there possible any renewals of your cost for patenting? So is it possible? Yeah. And the second, for example, for your invention, for your technical solution, you should understand is the reversal engineering is possible for your product or not. If the reversal engineering is possible, it's better to patent your solution, because in this situation, you disclose your invention in a patent application, but on the other hand, you will have right for exclusivity using. On the other hand, if your product is difficult for reversal engineering, it's in such situation, it's better not patent your invention, because in this way you give extra information for your competitors, and it will be difficult to understand is the competitors use your patent or just they use any other method for production, the similar product. Okay. So if you understand that patenting it's not your way, so you can select something in other options. The first, if in case if your product it's not available for reverse engineering, you can think about keep it in a secret, yeah, like a trade secret. So it's cheap because you don't need any cost for granting patent. so you doesn't reveal the invention. On the other hand, you have no protection against reverse engineering. It's difficult to enforce, and secrets often leak quite fast. It depends, but it sometimes occurs. The second way you can go is like disclose. It means publish the information. So it means you can you give the opportunity all people to use it, and actually it's a way for prevents others from patenting the same invention. So of course anybody can use your invention, but when you publish, nobody other can patent it and can prohibit your or other parts to make it. And the third options, do nothing. So there are some risks, yeah. So don't offer any exclusivity, and competitors will often learn details and so on, and the risk is high. So okay, if you understand that you need the patent to your application, so what you should do before filling the application? The first, you make some analysis and understand should you patent or not. So you try to understand balance between cost and benefit. Yes, what is potentially bigger. The second way, you should understand the prior art of your invention and understand is your invention really new and has inventive. And then you can have you clarified the rights to invention with the company and employees and business partners and so on. Okay, if you don't patent, somebody can make you patent. Competitors may take the advantages if you not patent your invention, and you lose any potential for licensing and transferring technology and so on. Okay. Also, patent it's very rich pool for information, for ideas, for R&D. For example, if you wanna search any ideas for directions of your R&D and for commercialization, real product, it's better to make a search in a patent base. For example, I worked in Samsung company in South Korea for 5 years, and I developed the cathode materials for lithium battery. And all information which I found in articles, it was absolutely not applicable for real production, for real business. And all ideas which has commercial potential, it's usually patented by big companies. For example, finally, in that project which we made in Samsung for 5 years, we invent innovative cathode materials which finally applied in Galaxy's 5 flagman model of Samsung. And it was patent, but not published in articles, of course. So any commercial ideas with commercial potential you can find actually in patents. Okay. The next object, IP object, I wanna tell you today. This is utility model. It's also named like a small patent because it's granted only for machines, only for products, not for methods, not for process. It has a shorter period of protection. It depends from 3 to 10 years. It depends. The holder has disclosed invention to the public, similar like a patent. But there are only 2 criteria of patenting. The first is new. Yeah. The second is technical application. So the third about not obvious, you don't need. So there is a scope of protection compared with the patents. So and utility models and patents has territorial IP rights. Utility models cover for 10 years. In case of patents, protection is up to 20 years. So publication, in case of patent, patent application published after 18 months, utility model published earlier. And in case of patents, you need inventive step. In case of utility model, inventive step, it's not necessary for granting a certificate for utility model. So, and we have already told about secrets. Yeah, it's like an alternative to the patenting. In case of patent, you disclose your invention and has any rights for monopoly. The other way, not patenting, but make it trade secret. So trade secrets, it's information is which is not generally known or easily discovered, has any business, commercial, economic value, because information is not generally known, and the subject to reasonably afford the maintenance security. So trade secrets, it's a good mechanism, and also it's a good mechanism for protection, for practical application, for example, for processes, in combining with a patent. For example, actually, I like to make a tea ceremony, and for example, I invent any method for producing tea with a wonderful smell and taste. Yeah, and I know that I need to take, for example, water for 70 degrees. Yeah, and saturate it for, for example, 5 minutes. Okay, if I want to patent this method, I will, when I disclose my method, I will not write exact temperature and exact time. I don't know. I will write the interval. For example, I write in a claims that I use water at the temperature from 50 degree till 80 degree, and the time saturation is from 3 minutes till 7 minutes, for example. And also in my patent, I will demonstrate that I obtain wonderful tea and at smaller temperature and at higher temperature and at shorter time and at a longer time. But the most wonderful tea I obtain at 70 degrees at 5 minutes. And these two numbers I will keep like a trade secret. So on the one hand, I will have protect for my method with intervals. And on the other hand, even this disclosure of my method, it's will give no advantages for competitors because they don't know the exact temperature and exact time. So combination, patenting and trade secrets, it's a good combination. It can make the strongest way to protect your IP. We have don't much time, so I will tell about shorter about trade secrets, and let's tell about designs, registered designs. Design is registered design. It protects the external view of your product. It's like any shape of Coca-Cola bottle, or, for example, if some designer has may make, for example, table with any one individual shape of legs, this shape he can protect like industrial design or registered designs. Of course, if we look at any car, any automobile, there are a lot of any parts with individual design. Yeah, it's like exterior, interior, any parts of wheel discs or any lighters and so on and so on and so on. So there are only two requirements for protection industrial designs. The first is novelty, and the second is individual character. So that's all. And you have exclusive right. Of course, protection for industrial designs also have a limitation by territory. What about duration? The maximum rights protection is 25 years, and unregistered design rights is for 3 years. The one important thing that shape, you cannot protect any shape of your product. For example, if your shape is it's like a shape of airplane flight. Yeah, it's like described not only design idea, but any technical necessities, like a shape of plane wheel or something like this. You cannot protect it like designs. So the next is trademark. Actually, trademarks we meet every day, very often. Yeah, it's usually it's a sign or graphic which distinguish your product or your service from the others. So if we see like a letter M of McDonald's or Coca-Cola, we have any association with service, product, company, and so on. And this is the main goal of any trademarks. So trademark different different kinds. It can be just sign, graphic, or it can be combined, like picture and letters and so on. And the main category is we need to trademark it's distinguish you from others. So your exclusive right for trademark has some limitations for territory, of course, and for specialty. It means if I register trademark, for example, for IT area, any other person or any other company can register similar trademark for any other area, for example, I don't know, for fruit selling. And one more important thing, images or any word which you'd like to register like a trademark, it should be has like imaginary type, not description type. For example, I cannot register trademark bread for any kind of these goods. For example, if we look at the image apple, yeah, we cannot register Apple View trademark for fruits, for example. On the other hand, for IT area, it's okay, because it's Apple for IT, it's not description category, but for fruits, it's description and it's prohibited. And the last thing, I think, which I repeat, that if we make any product, this product usually contain a lot of IP objects. Yeah, it's a trademark and copyrights and designs and patent and trade secrets. And usually, if you'd like to produce your product, you should remember about two important things. The first, you should make the complex protect of your product. It means you should combine patents and trade secrets, trademarks for your individuality on the market, and trade and registered designs for viewer of your product. This is the first thing, and it's good case. For example, in some medical, for example, application, maybe you know the any medicine. It's like Arbidol. Yeah, it's antivirus medicine, and the story of this medicine such that patent was granted in 1987, and after 20 years, it's stop protect the invention, but the company used combination patent and trademark. And after using trademark for 20 years in combination with the patent, so they had 20 years of monopoly, and they sell their product with a trademark. And after protection by patent, people usually go to pharmacy and asked medicine which they know. They asked Arbidol, and even a lot of generics occur after patent stop working. customer anyway asked Arbidol. So combination of IP, it's very good way to improve your value. And also in case of IP, 1 + 1 is equal 3, not 2. So it's always you always have a synergy. So 1 patent + 1 patent, it's like a force of 3 patents. This is the first thing. Make combination of IP objects. And the second, you should remember that if you have a patent, it's not a guarantee that you may produce your product. When you have a finished product which you want to produce and sell, you should check if any production stage or any product parts covered by patents of other parts. If it's so, you should go and discuss, can you use their patents or and add any conditions or something like this. And after that, and after you understand that all your production stage and using stage of product and parts of product, it's not infringement any other patents, it's okay, you can produce and sell and make money for your product. So that's all which I want to tell you. I will be glad to ask for your questions. Thank you.
Oh, any questions?
Thank you very much for your lecture, first of all. My question is on some of the rights that are granted by, let's say, a trademark or a patent. So you said it prevents other people from exploiting your product or your invention. And I was wondering, there's an advert that I saw not long ago that was made by Google, where they were trying to advertise their new phone, the Pixel 8, and then the advert was the Pixel phone was there and there was an iPhone, and then they were making these jokes. And then at the end of the video, they wrote in fine print that Apple is a trademark of Apple Incorporated, and so on and so forth. So my question is, before they made that advert, did they have to get permission from Apple to include their trademark symbols in their advert, or does the fine print that they added absolve them of any wrongdoing?
I see. The first of all, it depends on the purpose of using. Yeah, we should split commercial using and non-commercial. So if we are in the area of non-commercial using any rights, copyright or so on, it's not a problem. So this is first. The second, if non-commercial, but it make some any money lose or goodwill lose, yeah, it's also we should remember about non-commercial using, but application when the goodwill of company can fall down, it's also prohibited. So if we tell about commercial use, so it depends. In most cases, of course, it will be infringement. Yeah, and we should make lower risk and eliminate any risk of infringement any rights. For example, it's like a receipt. If you use any pictures for your presentation or something like this, it's you can check also in a Google search. You can search in pictures with any rights, for example, free use or use for non-commercial or something like this. Or you should, if you want to use any pictures for commercial using, you should buy it in any picture stock. But anyway, it's better before starting some way, it's better to check any rights you infringe or not. Володь, там и продолжение вопроса. Точнее, ну, давай.
Right. Yeah. Okay. Thank you very much for raising this controversial issue, actually. I think you said the speciality and territoriality is the two principles that base the patents. So do we have patents which are acceptable globally and can be prevented somehow? Otherwise, the patent that is registered in one country can be violated in another, yeah?
Yes, for example, if you have protect on one country, and don't have protection in other country, to using your invention in that country, it will not be any infringement of your rights because you don't have any rights in this country. On the other hand, if you, for example, you protect your invention in country A, and they produce the same products in country B, they not infringe your right. But if you wanna, if they wanna to sell these products to country A, it will be infringement because you have protection rights on this area.
Globally.
Unfortunately, we don't. There is no world patent. Yeah.
Okay, that's one. The first question is that. The second one is I want you to see in this presentation the most important phenomena that I've seen these days in Russia. Like I've seen companies like McDonald's or KFC and other Coca-Cola and so on has been somehow transferred into local companies.
Okay.
Is there any kind of such issues like property rights? Are they transferred properly or sold? Well, what do you know about this?
Yeah. So this in such cases there is a franchise mechanism works. So the idea is that company holder of the technology and the standards and trademarks, the first thing. So they can give the rights to any other company, a local company, which will be use the trademark and strictly consider these rules and all protocols and any management processes which described by a mother company. So it's a principal franchise that there is a holder of trademark and technology and processes and protocols. This base company give rights to use trademark with all protocols for any renewal. Yeah, franchise.
Because I see new company is a different trademark which produces products and services. And in this case, I think the patent has to be sold or transferred.
There are two ways. The first is approach is franchising. Yeah. The second it's like a yes, absolutely. You can change anything. Yes, and another approach. It's not franchising, but just licensing your technology for production or for any industrial company. For example, university usually make some innovations, but the level of development and innovation is around technology readiness level, it's around 3, maximum 4. But for real industry, real market, you need technology readiness level around 9, 8, 9. So, so for example, university usually make innovations, patent it, and give to industrial partner the rights for using this technology for any patents. So technology transfer in such way, it's usually works well.
Thank you. My follow-up question is predicated on what you said about non-commercial use. So I'm still very much interested in a scenario where, suppose I, as a private individual who has, suppose a social media account, maybe on Instagram or Twitter, suppose I get a video from a media company like Sky Sports or Supersport or whichever company, and then I transform their video and add some of my own, maybe animations or whatever that I add to it. And then in my video, in the caption, I link all the original sources of where I got that video. If I've added music to my video, I link the original artist. If I've used any images, I link all the images and put a disclaimer in my post saying, I do not own the rights to any of these videos and they belong to A, B, C, and D. In such a scenario, would I be liable for infringement? Or since I am a private individual who's not gaining any money from that Facebook post, would I be okay to do such a thing?
Mm-hmm. So in such situation, in most cases, it's not infringement. Of course, it depends on the license type. For example, translation of football match, yeah, soccer match. It depends. But anyway, if you take some initial video or initial right object and make it significant way, change it significantly. If your individual changings, your individual contribution in the final product, it's more than initial part, it's okay. For example, there are some stories that there is a old tale, and some modern authors take this story like a base, and based on this make new literature, new new copyright object, new story. But of course, they previously tell the base. If they change it significantly, it's not infringement. If the changings it's not so big, not so damaged, it's infringement. For example. Yeah.
Thank you for your presentation. For me, I would like to ask, like, there's some companies, like maybe we know like Apple products, and someone produce the products which are similar to Apple products, and for the name, like for Apple, we know it's like
Yes.
A-double-P, then he's like A-P-L-E.
I see.
And the same product. Okay, maybe not the same quality, but the same product.
Yeah, this is infringement. So in case of trademarks, there is a category is similarity. For example, the idea of trademark make your product or your company individual and distinguished from others. And for example, you have a trademark Apple, and I make the similar production and I write APL, for example. But anyway, I infringe because my image or my name of product is similar to your. And any customer which would like to select between your product and my product, he may be confused because of selection. Because when he will select my product, he can think that it's your. So anyway, if there are two trademark and any combination is similar to this, it's anyway infringement. For example, Adidas and Abibas and Adidas, it's anyway infringement.
Thank you for your presentation. I would like to, from your professional point of view, give me a suggestion. What happened, for example, in developing countries is that we are trying always to get more information about technology and open technology, and nuclear transfer of technology is a very crucial and important topic. So what happened is that when we are trying to contract some companies, for example, of lithium, that's the example was interesting. The companies just said, no, everything will be closed. Also, it is hard to ask about which kind of patents or technology they are using. But when we agree some documents, they just start writing or getting more patents or more rights when they are in situ, in the place where we are trying to develop our technology. So how can we improve or avoid these kind of issues we have as developing countries?
So the first point is if we wanna understand more about any company, yes, it's on the one hand it's very difficult because any license conditions, it's not public, and company don't like it, doesn't prefer to make publicity of it. On the other hand, actually, patent search, it's a good way to understand the R&D strategy of company. For example, you can analyze which patents and which patent application they are filled on which countries, and based on this, you can understand which is direction of R&D for example, for big companies, it works very well. Which kind of R&D direction it's the main for this company, which countries is the main market for each technology, is priority countries and technologies. So if you want to understand about company more, sometimes it's difficult. On the other hand, there is one additional to patent source. You can check the royalty.com, this site which combine conditions for license conditions for license for licenses like a royalty value and another values, and you can check it's like a base type of license conditions, for example, for your case. You can base on this also.
One question from me. So about these patents in country A and country B, for example, if you have a patent in country A for some medical protests or something like this, and country B produces it, and citizen of country A go to country B because it's cheaper, for example, to get this prothesis in country B and then go back to country A. So will be there any consequences for him to use the protests that produced not in country A but in country B, where no patents of country A?
Well, very good question. Thank you. So let's see. The first, if you make make a plant in country B and then come back to country A, you come back with it's an illegal implant for non-commercial using. This is first point. On the other hand, if you need any support, it may occur a problem because you have illegal. Maybe this is a problem. Actually, the similar situation may be not only with the implant, but any kind of perfume or IT. For example, it's not legal here, but you buy there and come back with not legal product. Yeah, actually, it's maybe a small problem, because anyway you use not for commercial purpose, but anyway you use contrafact product, and it may occur any problem with the technical or something, and also you can be stopped on custom, because on a custom check it may be stored like a contrafact, and you may be also like a prohibitor of rules.
Well, then thank you again.
Thank you very much.
So now we have a short break, and then we will have a testing. Презентация всегда